Thanks a lot for the invitation. Yeah, you'll have to stop me because I love to talk about this stuff. So like, just tell me if I talk too much. So again, yeah, my name is Valentin de Bortoli, and today, I mean, all of this is part of I've adapted some slides I used to for a course I used to give in Paris on diffusion model last year. So yeah, it's kind of an introduction to diffusion model and generative modeling. So I don't know the background of everyone here. So again, feel free to interrupt me at any time if you have any question, because some of the stuff that I'm going to talk about is kind of specific to machine learning, and like sometimes it can deviate from statistics and math. So yeah, again, feel free to interrupt me, especially because I'm going to talk about generative modeling, and sometimes like the setting of generative modeling, the problem that we are dealing with is not even super well posed. So, like just to set the record straight, if you need anything, just ask me. Okay. So diffusion models. Diffusion models are like the new, I mean, if you followed a little bit the field of machine learning and generative AI and like everything that has been, if you open Twitter these days, you will see stuff that is done with diffusion model, and it's something that is used for generative modeling. So I don't have a slide on what is the task of generative modeling, but I might do it just on the board here. Is it fine if I use it? Yeah, like that. Okay. So, what is the goal of generative modeling? So, generative modeling is this is really a sampling problem. So this is a sampling problem, but this is a very different sampling. So you will have access to. You're going to target some distribution pi, and you want to get samples from pi, right? That's the goal of sampling in statistics. But where it differs from classical statistics and statistical physics is what information we have access to for pi. And I'm going to explain exactly what it means. So let's say you do stats or you do statistical physics. What you usually have access to is you assume that pi has a density with respect to the Lebesgue measure or any reference measure, whatever. And you assume that you have a density of this form, right? And you have access to some kind of energy. And then, so U is going to be your energy, and then you're going to try to sample from that energy using, I don't know, Langevin or like MCMC scheme or whatever suits you. So the crucial assumption is usually that you have access to some kind of analytic form here. And it makes sense in physics, and it makes sense in statistics because we know what is the model we're trying to sample from. In machine learning, however, like we don't have access to this. We don't have access to U because the distribution that we are targeting, we don't know what they are. And the way we have access to pi is through a set of samples. So what I mean by that is that I don't have this explicit expression here, but instead, what I'm assuming is that I have, let's say, capital N samples, which are IID from pi. And then my goal is, and it kind of seemed like nonsensical at first, is that it's kind of like a bootstrapping approach in a sense that I only have access to these samples, and I want to draw more sample from pi. So the task you can think of is, let's say you have images of cats and dogs. So these will be your images of cats and dogs, and I want to sample more cats and more dogs. Okay, so that's the task of generative modeling, and as some application that you might have heard of are, well, like all these image models that are extremely popular, video models, audio models, where you have access to this huge data set. So basically this thing is going to be called the data set, like the set of samples. This is the data set on which I'm going to train my my algorithm on. And yeah, so you just assume that you have access to these samples, and that's it. And so usually the main task of generative modeling is first to curate a huge data set that is going to be representative of my distribution, and then leverage that to generate more samples. Again, so application in image modeling, video modeling, audio modeling, and something I kind of like as well, and we talk a little bit about that in the introduction, was the protein design. So protein design, let's say you have like you have a bunch of proteins. So we have this huge database of protein online that are usually experimentally given to us. And then we want to try to find new proteins which satisfy, let's say, you're going to target one specific type of antibody or one specific type of drug. Or like you want the very specific function for your protein. So that's the type of thing that we are dealing with. Again, we don't have access to you, and we only have access to a dataset. That's the setting I'm going to be studying here. So before I dive into what are diffusion models, I just want to maybe give you a little bit of history as well. So before, generative modeling has been around since the 90s, I want to say, even maybe before. And there were a bunch of competitors' approach to that that you might have heard of. And I'm not going to talk about them today, but they all have links with diffusion models. So I think one that is quite popular is called EBM. So this is an energy-based model. So this was probably the first one. So energy-based model, what you try to do with an energy-based model is you're going to try to fall back into this setting by estimating this. So basically, you're going to have like a parametric function that is going to try to estimate this energy function, and then you do and try to sample from this model, right? So that's the, and when I say parametric function, of course, what I mean is a neural network. That's the. So EBM, we had like a normalizing flow, which I'm not going to talk about it now because I'm going to dive more into the details later about how they are linked to diffusion models. And I think the latest thing before diffusion model appeared as like the latest contender was GAN. So GAN is generative adversarial network. Generative adversarial network, which is something that is actually quite different from diffusion model and all this stuff I've been talking about before, in that it relies on some kind of min-max game to try to solve the same task. So GANs were all the rage up until, I want to say, 2020. And then like there was this paper from, I think, people at OpenAI, diffusion models beat GANs. And since then, diffusion models have been the state of the art everywhere. Okay, so that's for the setting and the history part. Is there any questions so far? All good? Okay. Right. So I'm going to dive into why diffusion models have risen as something that is now used by almost everyone in the industry. And I think one of the main reasons diffusion models are so popular is because they are highly flexible. So I will give you, like, the goal today is for me to give you like kind of different point of view on diffusion models, so that even if you come from different background, at the end of the day, everyone understands diffusion models in their own way. But when you look at what you need to implement in practice, it's very simple, and then the sampling procedure is also very simple and very flexible. So the flexibility and the fact that it's also, we kind of know what happens, like there is some kind of, you can do some theory around it and you can control a little bit more compared to everything that I talked about before, is what is really attractive. And especially, like when you go to like Google, Meta, etc., something that they are really, really interested into is that these models scale very well. So that means that if you have huge amount of data, very, very, very high dimensional, these diffusion models work very well. And there is one key reason for that is called like iterative refinement that I'm going to explain. Right. Okay, so I might go to the next slide now. So yeah, that's just one of the stuff that, I mean, this was back in 2022. Now the models are even better, especially like OpenAI has like extremely good video models now. I'm not gonna pretend that this list here is exhaustive. There are like plenty new work on that, and it's a very, very fast growing field. Okay, so yeah, the video I'm of course not playing. Let's dive into how to do diffusion models. So again, yeah, I think if you're not happy with what I say and you want to check the paper, I think the first paper which introduced diffusion model was a paper by Saul Dickstein and co-authors back in 2015. And it was based on some kind of variational approach. So variational approach, so what I mean is hierarchical VAE, VAE for variational autoencoder. But it didn't work at the time. And it's only with these two papers by Song and Herman and Jonathan O in 2019 and 2020 that they made it actually work and like gave some kind of intuition of why it should work, etc. So the first introduction I'm going to give is based on this paper here, like the Song and Herman 2019. So I guess the slides will be shared later, so like you will have access to the reference as well. I will also give you my website on which like there are all the like on which you have like more content and like more slides, etc. So yeah, so what I'm going to present right now is based on this paper. And I'm gonna do everything first, like for the beginning, because it's Monday and it's early. I'm gonna do it without any reference to stochastic calculus. So everything will be like not very rigorous, but it will give you some intuition. And then if we have time, I hope we have time later, I will dive into how we can give somehow a more grounded presentation of diffusion models.
Do you assume samples are independent as a
Yeah. Usually we assume the samples are independent. Like, do you mean in the data set here? Yeah. We always assume they are independent. You will see, in fact, like this, I don't need to assume that they are independent. So this is just what I have access to. In fact, I don't need to know about the joint distribution of my data set. I just need to know that marginally they are all distributed according to pi. But the common assumption that we make, and to be fair, we never check if it's true, the common assumption is to assume that they are independent, just because, like, you know, this is the internet. Like we have access to images of cats and dogs, and we assume that they are independently distributed. But yeah. You will see, in fact, because what we have is just we need to compute expectations. So we'll just approximate expectation with this, and the only thing that we need to say is that, okay, this empirical measure will converge to the true expectation. So we just need that marginally we respect pi. That's it. Yeah.
What do you mean with this x in a circle?
Oh yeah, that means that they are independently distributed. Wow. That's exactly what it means. Yeah. It's like, you know, like when you have this, like that would be like for 2, and that if I have x1, x2, like they are distributed independently, and I just put it to the power n2. Yes. So what do we want to do? We want to sample from pi. Okay. So pi, you know, like it's the distribution of cats and dogs. It might be very, very complicated. Usually, so yeah, maybe something I can say is like I'm gonna keep taking this example of images and how do we represent an image? An image, you know, is we can see it as just a grid of pixel, and each pixel is a real value, actually in R3 because you have the RGB channels. Okay, so each pixel is a random variable in R3, and I have as many pixels as the resolution of my image. So usually you assume that you have something. Let's say if the resolution is 256 by 256, that's the dimension. That's the dimension in which I'm dealing with. So I'm going to assume that pi is a distribution on RD, and D is very large. That's the kind of setting that we're usually into. So we are in this setting where we try to sample from pi, and pi, it can be like very, very complicated. Usually, there is this thing called the manifold hypothesis that we assume that in practice, pi does not have a support on the full RD, but is in fact supported on some kind of underlying manifold. So all of that to say that pi might be extremely complicated. And so sampling directly from pi might be really, really hard, but something that we know how to sample from is a Gaussian measure, okay? So why am I talking about Gaussian measure here? So if, sampling from a Gaussian, we know to do that very, very well, even in very, very high dimension. And something I know how to do as well is if you were to give me some sample from pi, I can transform any sample from pi into a sample from a Gaussian measure. How do I do that? I'm just going to add noise to the image, or like to the sample from pi, until I reach some kind of Gaussian. So I will show you exactly how to go from here to here, but the important thing is that this is destroying information. Here I have a lot of information about the image, etc., and I'm just going to destroy it to reach a Gaussian. Okay, so that seems okay. Yes, we can do that. That's kind of useless to destroy information, you might say, but the kind of bet that I'm gonna try to show here, and I'm gonna try to show that it's true, that it works, is that we can actually go the other way around. So this is destroying information, and this is like adding information. So it's starting from a Gaussian. The whole goal of diffusion model is starting from a Gaussian. I'm gonna try to go back from, like, reverse this information destroying process to go back here. Okay? And the kind of crazy thing is that it works. And so that's why sometimes they are called denoising diffusion model. So the diffusion part in diffusion model is for this thing here, where I'm going to progressively destroy the information. And the denoising part, when we say denoising diffusion model, is because in fact we are removing the noise here from a Gaussian to reach back to the true data distribution. So this is what is shown here. So let's say you start from a mixture of Gaussian. You're going to destroy the information until you reach some kind of Gaussian, and then when you want to create new samples, you're going to start from the Gaussian and apply this kind of denoising process. So I'm going to explain exactly how we do these two steps here, but like high level idea is to do this. It's to just do some kind of time reversal. Yeah. And of course, the hard part is how to invert the forward noising process, right? So this is going forward in time, and this is somehow going backward in time. Right. So okay, as I promised, like in the first part, I'm going to do things with my hands and like not being like very, very rigorous. But again, this is just to give you the intuition, and then we'll see how we can formalize that. So I'm going to first define a noising process, something that goes from the data distribution to the Gaussian. And this is easy to do, right? There are many, many, many ways of doing that. I'm just going to choose one of them. But this is actually what is used in the literature, but you have like many, many choices to do this stuff. Like this is just destroying information. So the way I'm going to destroy information is I'm starting from the data distribution, and then I'm going to, for t steps, so this is a Markov chain, right? Like I'm going to apply a noising kernel. And the noising kernel is just a Gaussian where I'm just removing part of the previous sample and adding a little bit of noise, right? So this is basically like contracting for those who are familiar, this is the discretization of a Horstein-Uhlenbeck process, right? Actually, this is the integration up to time alpha of a Horstein-Uhlenbeck process. Okay, so this is just like, again, contracting the current input and adding noise. And you can show that this thing, as t gets larger and larger, this thing will converge to a Gaussian, right? So I'm stopping after t steps, so there is a little bias towards the Gaussian. It's okay. We don't really care about this small bias in practice.
Sorry, is it like a theorem that is proven?
Yeah. So I'll show it with the. I think I have slides later about how to do that. But yeah. So basically here, I think you would have some, you won't reach a normal Gaussian because you have the parameter alpha, you will have some bias of size alpha. But yeah, so basically this thing we can prove that it does converge to the Gaussian. And it's even clearer if you look at the Horstein-Uhlenbeck process because the only invariant distribution of the Horstein-Uhlenbeck process is the Gaussian with the you can compute the mean and the variance, etc. Right. So that's for the noising process. So the noising process, again, we just contract, add a little bit of noise. And now I'm just going to say, okay, so wait, I have this forward thing. Can I write it in another way so that instead of starting from time 0 and going forward in time, instead I'm going to rewrite it by starting from the last point and going backward in time, okay? So this is sometimes called ancestral sampling, and instead of starting from Q0, I'm starting from Qt. So again, Qt is So Qt is approximately Gaussian here. It's not exactly Gaussian, but like there is some bias again. And then I need to. The hard part is to compute. So this is going from xt to xt plus 1, and this one is going from xt plus 1 to xt. So this is, again, time reversed. So how do you compute the going from t plus 1 to t? Well, we have this nice thing called the bias rule that gives us that if I want to compute this backward kernel, I can express it as the forward kernel and the ratio of just the marginal here, right? This is just again, this is just the bias rule. Okay, so we are all set, and so if now just imagine for a second that we were in a perfect world and that we knew how to compute this exactly, then I would have an algorithm to sample from Q0, because I would just start from Qt. Well, I'm actually not really Qt. I would start from the Gaussian, and then I would apply iteratively this kernel, right? So again, if I knew how to sample from Qt given t plus 1, like the backward kernel, if I knew how to compute the backward kernel, the algorithm would be start from the Gaussian, apply the backward kernel for t step. I think there is a typo here. Here it should be t minus 1 as well or something. Anyway. Yeah.
Maybe it's an English question, but what do you really mean when you say destroying information?
Sorry?
Destroying information.
So let me check if I have a. Do I have a picture of this? Right. Okay. In the case of images, it's very clear because let's say you start with the image of a face, a human face. When you're going to apply this forward kernel, what you're going to see is that the face will disappear and you will add more and more noise. So the information about Q0 is being destroyed. That's what I mean by that. It's like this is not a very formal or rigorous statement. What I'm just saying is that at the end of the day, if I look at the terminal distribution here, it should be just Gaussian, and with the Gaussian, I have no information whatsoever about Q0. So that's what I mean by destroying information here. I don't know if that's clear or not. So yeah, again, like, okay, so if we had access to this backward kernel, the algorithm would be start from the Gaussian, apply the backward kernel until we reach back Q0. Of course, we don't live in a perfect world. So the problem is how do we compute this backward kernel. So I'm going to dive into this later, like in a few slides. But first, like I just want to say that the forward process, like I showed that it was a Gaussian thing, so like we can write it like this as well. And so that was your question. Like you can show that the distribution here actually does converge exponentially fast to a Gaussian distribution. And it converges exponentially fast. I mean, if you look at the Kullback-Leiber divergence, in the Wasserstein distance, in the total variation distance, whatever. Like it's very, and it's independent of the dimension as well. It's the Ornstein-Uhlenbeck process is basically the nicest process we can think of in terms of stochastic calculus. Right. So. Okay, so as I was saying, now we're gonna try. So there are a lot of equations here. This is just to give you some kind of idea of what is happening. But the main idea is again that I'm going to try to invert to compute this. And remember, I said we're gonna use the bias rule here, and the problem is, of course, that I have access to this explicitly because I just said that it was Gaussian. What I don't have access to is the marginal here, right? So I don't have access to the marginal, and the reason I don't have access to the marginal is because I'm integrating over the whole path when I need to compute this, and so this is something that is untractable. If I had access to this, then I could compute the whole thing here, and again I would have access to the backward kernel. So the trick that I'm going to use here, which again, it's not extremely rigorous here, but like just bear with me for a second, is that I'm going to rewrite this thing. So this is a ratio of the marginal at time k and the marginal at time k plus 1. So you can think that because I'm progressively noising my distribution, the ratio of pk and pk plus 1 are actually quite close. Right. This is just if one was a mixture of Gaussian slightly noise. Let's say that pk was a mixture of Gaussian slightly noise. Pk plus 1 will be just slightly more noisier, but the idea is that they are pretty close. Okay. So because they are pretty close, so here I've just rewritten everything as the exponential of the difference of the log here, and then like. I do some algebra to rewrite everything in more nicely in the exponential. And what I'm gonna say is that, okay, this is untractable. I really care about that, right? Because this is a distribution with respect to xk. So I need to know if I want to sample from this distribution, I need to know what is the form of this stuff. So this part is nice because this is Gaussian, but this part is not nice because it's completely unknown. So what I'm going to do is that, in fact, I'm going to find a Gaussian approximation of this stuff by doing some kind of linear expansion of this term. Okay? And the way I'm going to do it is as follows. The key assumption is to say, okay, remember, I had this difference of log here. Oops. I had this difference of logarithm here, right? So I have this difference of logarithm. I said before that pk and pk plus 1 were closed. And if you are on the trajectory, you can think that xk and xk plus 1 are close, are very close as well, right? Like I've just I've added a slight amount of noise, and I've contracted a little bit the input. Yeah. Am I? I'm sorry.
Yeah, and you also use like double index in there as well, like with the slash little pipe.
Yeah. So, okay. So I'm gonna clarify what I mean by all of this. Is there? This is. Is it this? Yeah. Whoop. Right, so what did I put up here? Okay, so when I say P0 n, x0, n, this means that I'm looking at the whole trajectory, right? So basically, I started from x0, and then I'm looking at the whole. Here I have x1, here I have x2, x3, whatever, and here xn, right? So when I look at this, that means that I'm looking at the distribution of the whole trajectory.
Within the denoising, or
So here, like so far, like I'm making no difference between denoising and denoising. This is just what I'm doing is just a rewriting of the because when you have something like this, I can write it either as p0, x0, and then a product of conditional distribution going forward. So this is the conditional of k plus 1 given k, right? xk plus 1 given xk. So this is like, this is just a rewriting of my Markov chain this is a writing of my Markov chain in a forward manner. And I can also rewrite it in the backward way, where now this is like the Markov chain is expressed like going backward in time. So this is the same distribution. Like all of this is the same distribution. It's just expressed like differently. Does that make sense?
so I'm still wondering, why do you need the double index, like one for the p and one for the x's?
So it's just because like if I mean this is just a notation point, but like I could write something like p of xk given xk plus 1. But like when I write it like this, it's just to kind of like emphasize the point that this thing here corresponds to going from k plus 1 to k. This is just that this conditional distribution, I'm just emphasizing the fact that this conditional distribution goes from k plus 1 to k, and that this conditional distribution goes from k to k plus 1. But like, I could just write it like this, and it would be like implicit. That's the. But yeah, I prefer to be like to hammer this point that we are going forward here. That this is the conditional distribution of what happened at time k plus 1 given k, and this is the distribution of what happened at time k given my knowledge of k plus 1, right? But I agree. I mean, like there are probably too many indices here, right? Right. So yeah, just to remind everyone. So again, the goal compute pk given k plus 1. I said that we have this Gaussian part that is nice, we like that, and we have this part here that is not so nice. My goal now is just going to simplify this stuff here. I'm going to simplify this and make some Gaussian approximation of that. Well, actually, I'm going to linearize that so that the whole thing becomes approximately Gaussian. Might seem crazy to do that because there is no reason for this to be approximately Gaussian. And in fact, it's true. I mean, in fact, you can prove that this approximation is not that crazy. But we'll see that later. Right, so, okay. So as I was saying, and maybe like just to finish my point here, when I talk about pk, so what is pk? Pk xk, this is the integral of p0 and x0 and on everything except xk, right? So dx0, dxk minus 1, dxk plus 1, dxk, right? So I just have like marginalized everything except for the thing that I actually care about. So that's why I could, like that's what that was again also implicit when I was doing this kind of bias rule. By the way, sorry, like I use P and Q like that's a typo that I need to fix. But like P and Q are the same thing here. Right. So again, like these two things are awfully similar. because I have this very iterative and very small modification during the forward process. So I'm going to do some kind of expansion here. The expansion I'm doing is saying that this is the first order Taylor expansion around xk plus 1. So what I'm saying is that this difference here is actually what I'm claiming and not proving is that this difference here is actually very, very close to taking, so if I do the expansion of log pk xk around log pk plus 1 xk plus 1, I will first, like this is the 0 term order and this is the first order term, right? And so what I'm going to do is I'm going to say, okay, so in what I had before, in this thing here, I'm just going to, I'm seeing that, I'm thinking of it in terms of Taylor expansion, and I'm going to replace this whole thing. I'm saying, okay, this is the 0 order term in the expansion, and I'm just going to replace the difference by the first order term. And if I just replace that by the first order term, what I get is this. Okay, right? So far so good. Okay, and I just replaced. So what I've done with this is that I've managed to. I had this difference of log pk plus 1, and I've replaced it by a linear term. But now remember that this backward kernel is just a function of xk. So what I really need to look at is what is this function in terms of xk? And this is, yeah?
Sorry, just a clarification. Is there a specific reason why I'm choosing to do the first order approximation at log pk xk minus xk plus 1?
It could be like around log, so here like it could be log pk plus 1 as well. It doesn't, what you would have, like you would have like other higher order term. When we're going to go to continuous time, there will be like no difference because pk plus 1 and pk will be like at the same time t. So that's why I'm being very loose with the notation here. If you want to do the proof correctly, I think you can use log pk or log pk plus 1. It will just add another term here based on how log pk varies across time. But yeah, that's a good question.
Question there as well. So if I read this gamma correctly, the second line reads as if xk is equal to xk plus 1. Then this expression is 0. But
yeah.
this seems impossible because you have pk and pk plus 1. Right? They don't know about each other.
Oh yeah, sorry. What you mean? If xk
is equal to xk plus 1.
The expression is not 0 because like here I have pk and here I have pk plus 1.
Yeah, but the right hand side of gamma I read as being somehow essentially the distance between the 2 points, or is
Oh no, it's an upper bound.
gamma is
This is not the difference between xk and xk plus 1. This is just an assumption this is just a loose upper bound on the distance between the two, like you would have, like in the so actually what you would have is because not only I have the spatial derivative, but I also have like the time derivative that occurs here. So that's why even if xk is equal to xk plus 1, you have this x. That's exactly the thing that we are talking about. Like, do you have this extra term? When I say you have the extra term in the expansion, that's the one that would come out as the time derivative. Well, when I say the time derivative, it's the derivative of p with respect to the small index. Okay, here, yeah, yes.
So this second equation is asking for the kernel to be, I don't know, some Gaussian or something like that.
This thing here?
Yes.
So this thing here is the the only assumption I would need for this to be true is some kind of regularity on pk.
Yeah. So this regularity is some sort of sub-Gaussian or sub-exponential hypothesis.
Yes. Yeah. So here, like for this to hold, this would hold under very, very strict and very restrictive assumption. When I'm going to move to the continuous time, in fact, it's like very general, and it can work basically for any distribution. And I'll explain why. And it can even work on like manifold. It can work on like arbitrary metric space and stuff. But just like if I don't want to use stochastic calculus, I have to go through this very, very restrictive assumption. That's the reason why I'm using. Yeah. Yes. So so I have my so now I look what I have in terms of xk here, and what I notice is that I have the exponential of something that this is quadratic here, and this is linear. So the whole thing is the exponential of minus something that is a quadratic form. So roughly saying this whole thing here now is a Gaussian. So what I've managed to do is that with my very restrictive set of assumptions, I've managed to approximate this backward kernel by some kind of Gaussian. Okay? So I started with something that was completely intractable, and now I'm ending up with something that is a Gaussian. And we like Gaussians because if I know the mean and if I know the variance of the Gaussian, I can sample from it. And again, as I said, if I had access to this backward kernel, I could just start from a Gaussian and then sample from the backward kernel. So the idea now is to say, okay, if I can compute the mean and the variance of this Gaussian, then what I just need to do is start from a Gaussian and then apply this kind of Markov chain with this very, very simple transition that is just, applying iteratively the Gaussian kernel with the given mean and given covariance, and then I will reach back approximately my target distribution, right? Of course, there is something not so nice here, and maybe you can see it, is that, yes, okay, I have a Gaussian approximation. So when I say, sorry, by the way, again, a notation point, like this notation means that this is a Gaussian with respect to the variable xk. This is the mean here. This is the mean of the Gaussian, and this is the covariance matrix. So the covariance matrix is nice because gamma was my step size in my forward noising process. So gamma, this is a parameter I choose. So this thing here is extremely nice. But if we look at the mean, like this thing is okay because I'm assuming I know xk plus 1. This is okay. This is okay. This is not okay because now I need to compute the gradient of the log of pk. And I told you earlier that pk is actually completely is intractable, right? Like pk is something I don't know because to know pk I need to be able to marginalize over this whole thing here. And I don't know how to do that. So here, yes, this is good. I have managed to write this thing as a Gaussian, so I'm already happier than I was 10 minutes ago. But I don't know how to compute the mean. And the whole thing now is going to find a way to approximate this gradient of the log of pk, right? And notice that so far I haven't talked about machine learning and like neural network and like approximation and like I haven't talked about that at all. And this is where it's gonna come in. So the only part when you need some kind of functional approximation is to approximate this gradient of log of pk. And here, just in terms of like trying to explain a little bit the literature, sometimes you will see diffusion models called score-based models. And this is because this quantity here, sometimes it's called the score. So the Stein score. So just a small point here, if you're doing statistics, this is different from the Fisher score. Because the Fisher, usually if you have a what did I put the thing? Oh, yeah. If you have a statistical model, you will have something that depends on some kind of parameter, and the Fisher score would be something where you differentiate with respect to the parameter, and here what I'm doing is different, right? Like what I'm doing here, I'm doing the spatial derivative. I'm taking the gradient with respect to x. Okay, so that's why this thing is called the Stein score. So the Stein score is just the gradient of the log with respect to x. Okay. Right, and this is what I'm going to try to approximate next. And yeah, so is there, before I dive into how we approximate that, is there any question? Is it kind of somewhat clear? Yeah.
Yeah. So again, everything here is in discrete time, right?
Yes. Yes. For now, like everything is in discrete time. I actually do find the continuous time simpler, but like it requires a little bit of stochastic calculus. So that's why it's for later today.
So maybe heuristic, why you said we're 10 minutes ago, happier than 10 minutes ago because we have a Gaussian now.
Yeah.
But now we have to calculate the gradient of the thing we don't know.
Yeah.
So is there an intuition why this improves our life as our situation?
That's slide 13. That's going to be the next slide. But I can give you already the answer. The reason for that is that we have we're going to be able to write this quantity as the minimizer of some kind of loss function, and then we're going to be able to use tools from machine learning, basically. So before, like we had the ratio to compute, and I mean, this is some kind of general rule that, I don't know, like through some years in machine learning, you understand that computing the ratio is in very, very high dimension, you know, like it's going to be not very well behaved and like you have this weird behavior. But if you go into log space, things are much, much better behaved. And if you take the gradient, then basically what you just need is to try to estimate some kind of direction. And so, like just from a heuristic point of view, I prefer to estimate this kind of stuff instead of estimating the ratio, because I know that the ratio might be, like if I have my functional approximator, this might be very, very badly behaved, basically. Like where someone could say, okay, instead of approximating the ratio, I could do the log ratio, but this is also quite complicated to do because you have the log ratio, so that's going to be a difference of log, and basically you end up with the same problem that like if you can very quickly hit like numerical instabilities with this type of stuff, and I'll show that this is much better behaved, basically. So yeah. Any other question? How much time do I? Okay, yeah. Right. Right. So the next part is we're gonna leverage. So to compute the term grad log pk, the Stein score, we're gonna leverage some literature in statistics that was mainly driven by Apo Ivarinen, so in the year 2000, about how to estimate this quantity. How to estimate, so Apo wrote a bunch of paper about how can we find like good estimator for this quantity. And the main identity, and actually the only identity I'm going to use, what is sometimes called the Tweedy identity, but also, I mean, it has many different names in the literature, so I'm going to call it the Tweedy identity, but you might know it as something different, which is going to express the grad log pk as some kind of conditional expectation. So I'm going to do the small proof on the blackboard because it's once you've seen it once, then it's like obvious what I'm going to do. So first, what is pk? Pk xk, I can write it as just the marginalization of P0k, so that what is this thing? This is the joint distribution of what happened at time 0 and what happened at time k, okay? So this is just this, and I'm marginalized with respect to x0, okay? So far, so good. This is just marginalization. Now I want to take the gradient. My goal is to compute gradient of log pk. Okay, so I know that gradient of log pk is gradient pk divided by pk. Okay, so I'm going to try to take the gradient of pk here. Gradient of pk. with respect to xk. What is this? This is simply the gradient of, sorry, I'm going to rewrite this one more time. So what is this? I can write it as P0 x0, pk given 0, xk x0 dx naught. Okay? So again, this is just writing the joint distribution as the marginal and then the conditional distribution. Right. Okay, so now I want to take the gradient of pk xk. So I differentiate with respect to xk. I'm not going to touch this, but of course I'm going to touch this part here. And what I have is that I have p0 x0. I have the gradient of pk given 0 xk x0 dx0. Okay? Right? So what I'm going to do now is I'm going to rewrite that using, that the gradient of the log is the gradient of the quantity divided by the quantity. I can rewrite this thing as p0 x0, pk given 0 xk x0, and here the gradient of the log of pk 0 xk x0 dx naught. Okay? And finally, I want to compute the gradient. What I want to have access to is not the gradient of pk, it's the gradient of the log of pk. So, and I'm going to use that the gradient of the log of pk is gradient of pk divided by pk. So what I have is that the gradient of the log of pk xk is the integral of the gradient of the log of pk given 0 xk x0, and here what I have is p0 x0 pk given 0 xk x0 divided by pk xk, and here dx naught. All right. But now what is this? I mean, I've wrote it like this for a reason. This thing is just the bias rule, right? So with the bias rule, this thing is just, in fact, p of 0 given k, x0, xk. And so by doing so, this is exactly what I've written here. You see that the gradient of the log of pk is the conditional expectation of what happened at time 0 given the knowledge of what I have at time k of the gradient of the log of pk given 0, xk given x0. Okay, so yeah, that was really nice, but why is that better than what I had before? The reason for this is, again, as I said, this thing here is untractable because pk is not tractable. But what is tractable is pk given 0. So why is that? Yeah, I mean, any idea why? So I said that this is not tractable, but this, the conditional distribution is tractable. So I mean, do you have any? Do you have like? Is it clear why? I'm going to explain, but like, does anyone has an idea why this thing is tractable?
Because we've done Gaussian unification.
Yeah. Exactly. So this pk given 0, I can just rewrite it as pk given k minus 1, pk, sorry, need to, where is it again? So this thing here, this is simply the integral of pk given k minus 1, xk minus 1, p1 given 0, x1 given x0, and here dx1 up to dxk minus 1. But all of this is Gaussian. All of the transition here are Gaussian. So in fact, this whole thing here is a Gaussian. So I can marginalize that however I want. And in fact, this thing here, this is a Gaussian. Right? So again, this thing is not Gaussian. This thing is not Gaussian, crucially, because when I look at this is pk given 0, which is Gaussian. Okay, so this is good. But I have the p0 x0, which is my target distribution, which is highly non-Gaussian, right? These are my images of cats and dogs. So this is not tractable, but this is tractable. But the nice thing is that we've managed to rewrite this thing, which is completely intractable, as a conditional expectation of something that is tractable, right? And in fact, I think I might have some slide later on about what is exactly the form of this, but it's not important. The important thing is that it's Gaussian with some parameters. We know the parameters, and I can compute exactly what is this thing. Okay, so it seems like a little bit of dark magic, because on the left-hand side, I have something that is untractable, and inside here, I have something that is just the gradient of the log of a Gaussian. So there is something going on here. I need to recover somehow the untractability on the right-hand side. And the reason for that, and why I'm going to recover the untractability, is because of this conditional expectation. So this conditional expectation, like just to give you a feeling of what it is, this conditional expectation is the conditional expectation of x0 given xk. So this conditional expectation is basically trying to predict what happened. You know, I have a noisy observation. I have the noisy observation xk, and I'm trying to predict what is the image of cats and dog that it corresponds to, right? So this thing here, you can think of it as a denoising operator, right? It's just telling you, okay, I'm trying to estimate, given my best guess at the moment, which is this kind of noisy image that might resemble or not to a cat or a dog, and I'm going to try to estimate what is the clean image. And this thing, you can see that this is actually a very complicated task, right? Like this is not the task of noising. This is the opposite task. This is the task of recovering the initial distribution. So this thing here, this conditional expectation, is what is hard to compute, right? That's the whole point. So tractable, untractable, and we recover the intractability here because we cannot compute this conditional expectation, because if we knew how to compute this conditional expectation, we would have solved the problem, basically. That's the main point. So, but we are already better off because at least now we have that inside the conditional expectation, we have something that is tractable. And I'm going to need one last step to get to something that is actually usable for us, and for which we're going to be able to, and with which we're going to be able to approximate this quantity. Okay, so far so good. Right. So the last step is to simply realize that if I have a conditional expectation, so that's now this is where I put my machine learning hat, and I want to estimate this gradient of log pk, right? And I'm going to choose a family of the way I'm going to estimate this gradient of log pk. If I think in terms of machine learning, is I want to find a loss function. I want to find something that I'm going to be able to minimize, so that the minimizer of this loss function is the gradient of the log pk. But the nice thing is that I have managed to rewrite this thing, like this thing here, as a conditional expectation. And there is the nice property of the conditional expectation, I mean, under some assumption that I'm leaving aside for now, that if I have a conditional expectation, you know, the conditional expectation is just the projection on some space. And so it can easily be written as a minimizer, right? So the thing I've written here is that if like if you have a random variable that can be written as a conditional expectation, then you can just write it as a function of this random variable, where f is the minimizer of this function here. So this is just again by property of the conditional expectation, because the conditional expectation is of x given u is just you take all the information that you have about x, and then you find what is the best approximation of x given your knowledge of u, and this is how you can define. I mean, this is one way to define the conditional expectation if your variables are square integrable, which I'm happily going to assume for now. Right, so knowing that fact, I'm going to apply that to this expression here. Okay, so what does it mean in our case? In our case, it means that we try to compute this thing here. So my y variable is going to be this gradient of the log of pk xk. What is x here? X is this thing, gradient of the log of pk given 0 xk x naught. And what is u? U is just xk. Okay, so I'm literally like just applying this thing here. Now if I apply this result that I had before, I can see that the gradient of the log of pk is the minimizer of this function, where f is a suitable function. Okay, so I haven't said anything apart from rewriting this in another form as a minimizer of this thing here, of a quadratic function. Okay, in some functional space, right? But now the nice thing is that, and this is like really where the 3D identity shines, is, so I'm going to rewrite the thing here. So gradient of the log of pk is the argmin of f of the expectation of f of xk minus the gradient of the log of pk 0 xk x0. And here, the expectation is taken on the joint, right? It's taken on x0 xk. So again, as I said before, this thing here is tractable. This is just the gradient of the log of a Gaussian. This is the gradient of the log of a Gaussian. This, the f, this is just the family of function that I'm going to choose. So in practice, this thing is going to be a neural network, but like this you can think of like any approximator that you would like to input here, and on which you're going to be able to run this minimization. The nice thing compared to what I had before, so remember before what I had was that I had this conditional expectation that was nasty, right? The conditional expectation was not so nice because I said that it was the conditional expectation of what happened at time 0 given my knowledge of what happened at time k, and I don't know how to compute that. But when I write the argmin like this, what the expectation that I see here, this expectation is on the joint. So now the expectation is not, it's not an expectation of what happened at time 0 given what happened at time k, it's an expectation on both things. And I can compute that in like how do I sample from this? Well, I could sample from this by first sampling from pk and then sampling from this, right? I first sample xk and then I try to denoise, and then I would have like my sample x0 xk. But again, like I'm repeating myself here, but like this thing is intractable. But there is another way to compute this thing, right? another way to compute this is simply to sample from P0 and then to noise, to use the forward kernel that was like Gaussian. Okay, we said that this was Gaussian. To sample from this, and then I have access to a sample. So here you could say, well, hold on. We don't know how to sample from this. Like our whole point is to try to sample from P0, where P0 is the target. But this is where I'm going to use the assumption that I've erased, which is that we have access to a data set, right? So instead of sampling from this, I'm going to say, okay, I'm going to take one of the samples from my data set. I'm going to take one sample, one image of cat, one image of dogs. I'm going to noise it. And this is going to be my x0, xk. And this is going to be my Monte Carlo approximator of this expectation. Right? That's the whole point, that's the whole thing that we are doing here. So at the end of the day, do I have the exact expression? No, I don't. Okay. So I'm going to write it. Yep. Okay. At the end of the day, what I have is I want to find again grad log pk, which is the argmin over all function of this thing here. And what I'm going to do instead is I'm going to find like f star, which is going to be the argmin over all f of what? Of here. I'm just going to sum over all samples of my data set. So xki minus gradient of log of k xki x0 I, where here x0 I is just this is a sample from my data set. Sample from data set. So like cat, dog, whatever. And xk I is just some kind of Gaussian. So I don't compute exactly what are the mean and the variance are completely tractable. Yeah.
A question to the stuff on the slide, the first slide.
Yeah.
You have this U that you use. What's the intuition behind the U?
I mean.
What is it? Where does it come from? Because I missed it in the previous slides.
No, so like the U. No, sorry, yeah. So that's just like there's just a dummy variable that I use just to state that result, basically.
But what
So,
do you denote with U?
so here, like just if I make the connection, so y is the gradient of log pk xk, x is this thing, and u will be just xk. So I mean, this is just like a general result that I apply here. This is just
Okay, fine.
yeah, this is just so actually here, to be completely clear, okay, I'll say a little bit more about this like right after I'm done with this result. But yeah, so just to finish with this thing, this is what we are doing in practice. In practice, we want to approximate log pk. The way we approximate log pk, we choose a family of functional approximator, aka a neural network, and we're going to try to compute the minimizer among this family of functional approximator of this thing here. And this thing I can compute because this is just picking samples from my data set and noising them. Right? And this I can add, everything is tractable here. I just need to be able to do this minimization. And you know, like we have like tons of tools to do this type of stuff, like when we try to minimize over a function. So yeah, that's what we do. And the only part where you have a neural networks that come in is because here in practice again we choose here a neural network. So this will be parameterized by some parameter theta, and to do this stuff, we apply some kind of gradient descent algorithm or like Adam or like whatever optimization algorithm that you like on the parameter of this stuff to try to find the minimizer. Yeah.
Yeah. Are you using the same F for all the Ks?
That's a very good question. So actually, I was going to talk about it, but like, yeah, exactly. So there is one key difference is that this thing is indexed by K as well. So in practice, what we have is not that exactly, but we also, so this is the, yeah, very good point. Wait, sorry, like there is a, okay, I'm going to call that M, and this is N, right? Like, so I have N step and I have N points in my data set, right? So yeah, we not only do that for like all the points of the data set, but we also do that for like all the time steps in the chain, because we need to approximate grad log pk for all k. Right? Yeah, good point.
So K is considered also a continuous variable?
So here, like, what I've done is it's not a continuous variable because I've presented everything in discrete time. In practice, though, we consider it as a continuous variable, and when we do this, like we sample, you know, because this thing here, we sample it. In fact, I mean, okay, like this is later we're gonna write that in fact as an integral between 0 and 1, and this is just going to be a small t here, and here we're gonna have dt, and so what we do in practice, we just sample a uniform random variable between 0 and 1. So yes, this thing is in fact going to be continuous in practice, but like just for now, it's discrete. But yeah. Right.
One question.
Yeah.
Where does the k in the bracket come from? Because before we just said f of xk. Yeah, exactly. Where does the k come?
So this is just because so far, when I have done this f is only valid for this pk here. And basically, I need one f for every pk. Because I need to do this approximation for all the different k, right? So I can, you know.
Why does the k appear as a factor in the bracket?
I mean, this is just what I could have written is just like fk, and I call that like, you know. This is just a notation to say that I need this thing differently, and I just put it like as I just put it as another variable in. Yeah. Sorry. Yeah, that's yeah. It's a comma. Right. All good? Yeah.
It seems like you're performing a sort of regression, right? Where your input variable is xk, and the output variable is this gradient log pk eigenvalue. But when you actually do this optimization, you said you sample from the joint log x0 and xk.
Yes.
But you do it in the forward pass. So
Yes.
Your xk depends on x0.
So, sorry, I'm not sure I understand the questions, but yes, yeah, I mean, like, you're totally right that when I do the optimization, I first sample x0 and then I sample xk.
But isn't in the setting of a regression, your input variable is xk, right? Shouldn't your x0 be xk? But although you explained that it's intractable to get the conditional distribution of x0 to xk. But it seems like it's kind of cheating to me.
I'm not sure I follow because I mean, like, it's like basically what I'm only trying to do here is like I get something that is noisy, like a degraded version of x0, and I'm trying to recover the right version of x0, right? That's just yeah. I'm
about your sampling method for computing this
yeah.
this loss function.
Yeah.
So I would say that I mean in the regression setting, your x0 in this case is your output value, because you need x0 to compute the gradient of the log of p k of x k in x.
I mean, do you agree that here this expectation is computed over this, right? This is the expectation over the joint.
Yeah.
So the expectation over the joint, I can sample, I have two ways of sampling from the joint. Either I sample first from xk and try to estimate x0, or I sample from x0 and then compute xk.
Yeah, I understand.
But what I'm just doing is I'm saying, okay, I'm going to sample from x0 and then sample from xk. I agree that like when I'm doing that, because I'm only using my data set, like here there is a bunch of approximations that are going on.
My question is, isn't the expectation taken over the conditional distribution of x0 to xk?
Like the minimizer of this, yes, it's going to be the conditional, like the minimizer of this thing.
I mean, you said that you take the expectation over the joint law.
Yeah.
But I say, wouldn't that be the expectation taken over the conditional distribution of x?
No. Here it's really over the joint. So if you take this, you can really because it would be wrong if this was also depending on x0. But because this thing is only dependent on xk, the minimizer of this, like the proof to show that the minimizer of this is the conditional expectation, you just expand everything, and then like you can use the tower property of the expectation, and you're gonna see that the minimizer, when I'm saying this, like there is no approximation. Like this is true that the minimizer of this is the conditional expectation of x0 given xk. But this is because this thing here only depends on xk. Right? So I mean, we could do it, but like the main point here is that like you do the expansion. You do the expansion, right? So you only care about the variable f. So you will have the norm square of f. And then you don't care about the norm squared of this stuff because it does not depend on f. Then you have the cross term. And the cross term, like it's f scalar the gradient of log pk given 0 over the joint, right? But okay, I'm gonna do it because so when I expand this stuff, I have I have this thing here, right? And the other term I care about is going to be 2 times the gradient of f of xk grad log pk given 0 xk x0, this thing here. So this is still on the joint here, but I can rewrite that as the expectation of the square norm of f of xk minus 2 times, oh sorry, there is no gradient here, my bad. Minus 2 times f of xk. And here, this is where I'm using the tower property. This is the conditional expectation x0 given xk of the gradient of log pk given 0. Right? And so when I minimize that with respect to f, right? Like this is just you take the functional gradient, you do recover that this is the minimizer. So the minimizer is really this conditional expectation here. Okay? Okay, cool. Up. Other question? Okay. So either everyone is really confused or this is very clear. That's just. Right. So I have like what, 5 minutes before the break?
Sounds good, yeah.
Yeah. Okay. So I'm just going to might just summarize what we've done so far, and then I'll continue with some more derivation. But just before we stop, again, I'm really hammering this point, but to be fair, what we've done so far, it's already all of diffusion model. Then what I'm going to talk about is like kind of other point of views on this stuff and like tricks to make it work in practice, etc. But like the kind of theoretical grounding of diffusion model, this is what we've seen so far. So in 1 hour and a half. So, So, to summarize, we had the forward process. So the forward process was P0, X0, and then I had this thing going forward, okay? What I said is that, in fact, I'm going to do some kind of to sample, I'm going to do some kind of ancestral sampling where I'm going to start from, well, I'm going to try to be more consistent with the notation, where now I have this. Right, so I said that this is approximately Gaussian. So I can sample from this. Then I said, okay, we need to compute this. This was like hard because I had access only to the bias rule and it was something that was highly non-Gaussian, blah, blah, blah. Well, actually not that non-Gaussian, but like non-Gaussian. So what we did is first we had like this kind of Taylor expansion to have that pk even k plus 1 was approximately Gaussian. So that was the first step. And then what we notice is that the mean of the Gaussian was untractable. Right, the mean of the Gaussian was untractable, and it depended on the gradient of the log of pk, which is called sometimes the Stein score. And then the last step was to see, well, two steps actually, was to write grad log pk as a conditional expectation. And then use the fact that if I have a conditional expectation, in fact, that gives me access to a loss function, i.e. that this thing, in fact, is a minimizer of some function. Is a minimizer. And then, so we have a minimization problem. Right. So that was the whole story. We want to do this stuff, and to do this stuff, we needed to go all the way to get to something where we just have a minimization problem at the end. And what I haven't talked about is how do we solve this minimization problem? That will be like kind of the realm of like, you know, deep learning, machine learning algorithm, how we do it in practice, although people have tried to do like other stuff. There are some more, I won't say like more principled functional approximation that have been proposed. But let's say, you know, if you look at the images that are produced by these extremely good models, that's usually given by this by some kind of neural network approximator, right? So this was the whole thing, and so far, this whole process is what we're going to call, is what in machine learning we call the training, because basically what we are doing is we are training this kind of, you know, this functional approximator. We are training a bunch of functional approximator fk to approximate grad log of pk. And the reason, again, we want to approximate grad log of pk is to compute this thing with ancestral sampling. Once we have all that, then we are ready to go, because we will be able to just sample from a Gaussian and then apply this kind of Gaussian transition, this approximate Gaussian transition backward, right? Is the picture kind of clear, at least for now? Okay.
And the neural network is not used in the denoising part?
Yes, it's going to be used because it's used because so when we want to sample backward, we want to sample from this. So we start with xn, which is from pref is the Gaussian. So we start from the Gaussian, and then we apply that autoregressively. And here we replace this by the functional approximator that we have. So here we apply the neural network. That's where. So this will be like, this is why I call that the training. Then this is really the sampling part. So really, what we do in practice, we separate the two. first we have this training procedure where we only need to have access to samples from the data set. We noise them to try to recover this function. And then once we have trained that, we freeze everything. We have our big neural network that costs a lot somewhere. And then we do that to like sample new images. And that's really how it works in practice as well. Yeah. Yeah.
So a long time ago, I worked with BSDEs or backwards stochastic differential equations. So this projection here is a simple BSDE, right? A linear, yeah, it's trivial somehow, just conditional expectation. Is there BSDEs?
Yes. Yeah. So there is. So actually, this was pushed a lot by some people in Georgia Tech. So Evangelos Theodorou, and like some Yongxin Chen and co-authors. There is a way to recover. I actually didn't put it in the slides, but like there is a way to recover the loss function that I have. You can see that as computing the log likelihood of. Actually, it's not BSD; it's like FBSD. So forward backward SD. But yeah. So you have there is an interpretation of that in terms of BSD, and all of this in fact can be reframed as in terms of stochastic control, because this thing in fact is the control. Like if you look at it in terms of SD, this will be like the control term in fact. It's so yeah, like there is. This is really interesting. Like there is like a really strong link between all of this and like control stuff, especially. I mean, this is more my stuff, but like if you want to move away from generative modeling and you want to impose constraint at both ends, then you move in fact to you're gonna have like optimal transport is going to arise, and then you have like links with stochastic control. But yeah, like all of this is really linked to this kind of BSD, FBSD type thing. Yeah. Right. I think we can stop. Okay, so we're back. So in the next hour or so, we'll first finish a little bit, telling you a little bit more about this loss function, because there is maybe some stuff that I can tell you to get some more intuition about what happens when you do this minimization. So I will finish with that. And then I will present you another point of view on this model that was the original point of view on Sang and Hermon in 2019. Just before I do that, like, is there any question that might have arisen during the coffee break? No, all good. By the way, yeah, I got a remark earlier that this is, if you look at, I won't say modern presentation of diffusion model, this is not usually how it is introduced. Usually it's either introduced with the concept of hierarchical variational encoder, so I will touch a word about that, or it is introduced with the concept of like forward and backward stochastic differential equation with like with the notion of time reversal, and I will also explain that later. Again, like the why I introduced it that way, and I had all this kind of nasty approximation was just kind of to, even if you don't have any background in machine learning or stochastic calculus, I think this is just like manipulation of Gaussian stuff. So yeah, that's why this is a little bit unusual compared to what is done usually in the literature. All right, so yeah, let's have a look a little bit more at what is happening here. What am I actually doing when I'm minimizing this loss function? So I'm just gonna rewrite, I think it's in the next slide, maybe I don't need to do it on the blackboard. Yeah, well, I'm going to do it on the blackboard anyway. So one thing that we talk about denoising diffusion model. Where is the denoising happening here? And the denoising is in fact hidden in this stuff here, and I'll show you why. So I told you that pk given 0, now I hope that you believe me, that this is xk given x0, this is a Gaussian, okay? I told you this is a Gaussian because this is just applying a Gaussian kernel a bunch of times. This is a Gaussian, so this is a Gaussian in the variable xk with a mean with a mean that depends on x0. Again, the mean is explicit. It will be, I will give it to you in the next slide, but it's just, the expression is a bit nasty, so I just write m of x0 just to denote the mean, and the mean depends on x0, right? Because it's conditional on x0. So here I have a Gaussian kernel with a mean that depends on x0, and actually I have some kind of covariance, and turns out that the covariance does not depend on x0. And again, all of this is explicit. I have analytic expression that I will give you in the next slide. Right, so if I write this, what is this? This is proportional to the exponential of minus xk minus m of x0 squared divided by 2 sigma squared. Okay, this is just a Gaussian. And if I take the gradient of log pk given 0, so sorry. First, if I want to get a sample from this, again, I mean, I'm saying very stupid things here, but if I want to get a sample from this, I can write it as xk. I take my x0 and I add some noise here, where the noise here is just some kind of Gaussian, right? So this is just sampling from the Gaussian. Okay, and if I want to take the gradient of the log of pk given 0, xk x0, what is that? So this is just going to be, so how do I write this? Yeah, okay. So this is just going to be m. This is the gradient with respect to xk, again, here that I'm interested in. So this is just going to be m of x0 minus xk divided by sigma squared, right? Okay. So far, so good. And how am I using this? Well, I'm using this here, right? And I'm taking the expectation over x0, xk. So when I write my loss function, this is the expectation of f of xk, and then I have minus this gradient of the log of pk, pk given 0, evaluated at xk and x0. So this is m of x0 minus xk divided by sigma squared, right? But now what I can also do and what I can realize is that, wait, I said that xk is m of x0 plus sigma z, right? So in fact, I can rewrite this thing by replacing xk by its expression, and what I end up with is that I just have that this is f of xk plus z divided by sigma squared. So, in fact, when you're trying to do this thing, when you have this thing here, what you are trying to do is you are simply saying, okay, I want my function f. I'm given x0. I noise it to get to xk. I noise it with some noise z. And I'm going to try, given just the knowledge of xk, I'm going to try to recover the noise that I added to go from x0 to xk. Right? This is exactly what I mean, like up to some kind of scaling here. But like this is really what I'm doing. So this task here, this is called this is estimating what we call the residual, right? Because the residual is just the difference. The residual is just is what we call the difference between xk and m of x0. So the loss function that I have written is just estimating, trying to estimate this noise. Yeah.
Just to be clear, does the m depend on the k?
Yes. Yeah. Depend on the k, and this also depend on k. Yeah.
Thank you.
Okay. Yeah. So everything depends on k here. So that's my main point here. When we have this loss function, what we are just trying to do is we are just trying to estimate the residual, and so this is what people call sometimes the noise estimation a loss function in diffusion model, but something that can, if you read the literature, something that people also do is really to do a denoising, oops, no, the other way, is really to do a denoising task, because, so my goal is to estimate this Z divided by sigma k. But I could consider another loss function that would be just something like this. So this one would be really a denoising loss function, right? So I'm going to take another notation, let's say f hat, okay? So if I consider this loss function, now I'm not trying to estimate the noise, or the scaled version of the noise. What I'm trying to estimate is directly x0. So the task for this thing is just, okay, I give you xk, what was the denoised version of it? And then if, let's say that I get f hat star, sorry for the dirty notation, but like this is just temporary. If I have this thing here, which is the minimizer of this, how do I recover the gradient of the log of pk xk? Well, you know, the gradient of the log of pk xk, you know, I told you that it was the conditional expectation of the gradient of the log of pk given 0, and that was simply m of x0 minus xk divided by sigma square. So I have access to xk, and what I'm just going to do is I'm going to replace x0 here by, well, sorry, this is like x0 minus xk given xk equal xk. And what I'm going to say is that, okay, this is actually m of f hat star of xk minus xk sigma square, right? So what I'm just saying is that either you can just estimate the noise, so estimate the residual to estimate directly the score, or you can have really something that is a denoising loss function, and then you can plug it back to get this thing. So this thing is sometimes called the x0 estimation. And the other thing here is called sometimes the epsilon estimation. So it's just in terms of names in the literature. By the way, you might complain that here, like, why am I allowed to do this? Basically, I have interverted the conditional expectation and the function m. The function m is linear, in fact, so that like everything is fine, right? Like, that's why I have no problem doing that. But yeah, this is just to emphasize the point that when this loss function, you know, we took kind of a big detour to go there, but it's just a denoising operator.
Very naive question. I would expect like there something like x not 0 but k minus 1. Is it like completely wrong
You mean
idea? In the first line.
Here?
Yeah, the second thing that you subtract, I would just expect x minus k minus 1. Not k at x0. So why do you have there this x0 estimator? So why do you care to know the?
You mean this? Like, why do I have xk here?
The one line up.
This thing?
Yeah, exactly. Why do you have there x0 and not xk minus 1?
Right, because here, okay, this could be possible as well. It would give me another loss function. So there is a deep reason, like, okay, so everything that we've done so far, you know, I was using the joint distribution between x0 and xk, but I could have been using the joint distribution between xk1 and xk with another k1 in the trajectory. The reason why we do x0 and xk is that this thing is more stable. If we do xk and xk minus 1, we quickly hit like numerical instabilities because basically we're trying to estimate a very small change, and neural network don't like that. So here, like when I do this, the thing I'm estimating is the conditional expectation of x0 given xk. What you are suggesting is doing something like this, and this is valid, and it can work. especially let's say now that for some reason you didn't choose forward, you don't have access to this. Let's say that you don't have access to this because you don't have Gaussian transition, but let's say that you have access to this. That is something that arises. Let's say if you start working on manifold, there is no equivalent. Well, what is the equivalent of the Gaussian on the manifold? Sometimes it's hard to do, but you can still have access to this kind of stuff, but you don't have access to the whole thing. So you use this thing, and then we can do what you are proposing. It comes down to like numerical stuff at the end. Yeah. Other question? Yeah.
Maybe related to this, so couldn't then, because we choose the noise schedule, we convert this exponentially fast, could we renormalize and adjust the scale basically of the transition so that we estimate always like a normalized version?
Yes, yeah. So there is one paper that answers exactly your question. It's a paper from people at NVIDIA. It's called Elucidating the Design Space of Diffusion Model. And what I've said so far is kind of like the naive way where, like I haven't really cared about what is the scaling of the loss function, what is the scaling of the input, what is the scaling of the output, to go into all that nitty-gritty details. You look at this paper, it's in Appendix B6. I remember it by heart. But in that stuff, like they do exactly what you propose. Like they rescale everything so that every time for all k, you basically have something that has, that is like normalized in a way. And it's this thing is like great. Like it's kind of like deriving everything that I've said like from first principle in a very kind of machine learning way. But it's actually very intuitive the last they end up at the end. All right. Right, before, so this is, again, like all of what I've said. So this is just the analytic form of what I was saying before. When I promised you that everything was tractable for the Gaussian, this is like the full expression that you have when you compose all the Gaussian kernel. So this is kind of ugly, but the important thing is that that's exactly what I was writing, that when you look at the gradient of the log of pk given 0, xk given x0, this is just minus the noise divided by sigma k. And sigma k, I have it explicitly somewhere. It's written here. And zk is just a Gaussian random variable. So so all of this is just like to give you so you can trust me that I actually did the derivation, but that's basically what I was presenting you on the blackboard. Before I dive into the original interpretation of Song and Herman, I just want to take a quick detour with another formulation of this loss function that is quite useful in the case where you're doing like some more fancy stuff. So let's say you are dealing, for some reason, because you are dealing with some kind of physical process or whatever, you don't want to use a Gaussian noise. Because right now, there is a very natural question, which is like, why do we use a Gaussian noise? And the reason why we use a Gaussian noise is because it works. And it's very simple, and it's everything is Gaussian, everything simplifies, I have access to everything. So, but like there is no like very physical intuition of why like Gaussian noise is the best thing to do. And actually, for the past 3 years, a question that always comes is like, could we do something better? So far, there is nothing really out there, but there are some cases where you don't have access to a Gaussian. So the thing I was saying, for example, when you are on the manifold, like finding let's say you're doing some stuff on, well, the sphere actually would work, but like, let's say you do something like on a fancy manifold, which is the case if you do protein design, then you don't have access to the Gaussian because the Gaussian does not exist, and you don't have access to this transition because this transition is not Gaussian, right? So what I'm saying, and you really need, and to compute this thing here, the crucial part was that you needed to have access to this. So in just the next slide, I'm going to show you an equivalent loss function that is that doesn't require to have this and only requires you to have like samples. So you will only need sample of xk. So again, this is not, the next slide is irrelevant to generative modeling for image, video, etc. But it's relevant if you have like other things in mind. And again, this is due to Apo Ivarinen.
And how do you choose in other specific cases the distribution that you have as a reference distribution?
Yeah, so for example, on a, so I was mainly, for protein design, we usually worked on a joint space, which is the position in space of the amino acids of the protein, and also the frame, so like the orientation. So it's a problem that is in R3 times SO3 to the power n, where n is the number of amino acid. So we need to define a reference distribution on SO3, and because this is a compact manifold, we can just use the uniform distribution. And so that's why. So in that case, we can define an equivalent of. Here I was talking about the Ornstein-Uhlenbeck process that will converge to a Gaussian distribution. On manifold, on compact manifold, we use the Brownian motion because the Brownian motion will converge to the uniform distribution on the manifold. So that's that's what we do. Yeah.
So you said that we use the Gaussian, but if I understand correctly, like this is the Gaussian in the image space, right? So
yeah.
R3 to 56.
Yeah, yeah.
But so this is just like one base. Why can't I go to the like 2D frequency space and then do my denoising there and then come back?
You can totally do that. So
does it work?
It works. So I mean I worked on that. I was working when I was in Paris. I was working with Stéphane Mala. So we did a wavelet version of that, of course, and it works. And so you can change the basis. But to be fair, like you don't gain that much by doing that. Something that is very popular and that really works well is to go to latent space. So you first train a big VAE to kind of reduce the dimension, and you do the diffusion model in the latent space. The main reason for that is not because it gives you better visual results, it's just because you reduce the computational load because you will kind of compress the information. But you can totally imagine like, I mean like there are a ton of paper like changing the forward process, changing everything, and it's just like, it becomes like very application specific. And if you look at very, let's say, image, there is not much to be gained from doing that, at least for now. Like maybe in 2 weeks it will be different, you know, when the literature moves quite fast here. But yeah, that's the, yeah. There is some intuition that when you add noise, you know, we know what happens to the frequencies. Like the high frequencies are going to be destroyed first, and then the low frequencies. So when we design the schedule, like when we design how fast we noise, we have a little bit of control, but okay, we have a little bit of intuition. Okay, this is how I destroy the high frequency. This is how I destroy the low frequency. So adding the Gaussian noise, because it corresponds to like, you know, some kind of convolution with a Gaussian kernel, so like kind of blurring the distribution. We have some information about what it does, but it's not crystal clear if it's the right choice or not. Yeah. Yeah. Okay. So yeah, I'll just present you what is the equivalent form. It's more kind of like to satisfy your insatiable curiosity than anything else. So the other form is the following. So you can use when you develop. How you get to the other form of the loss function is you take this. I'm going to develop the square. So when I develop the square, I just have the square norm of f. I have the square norm of this, but I don't care about it because it does not depend on f. And then I have the cross product. I have the scalar product between these two terms. Okay. And what I'm going to do is I'm just going to simplify the scalar product. So you see that the scalar product that you need to compute is this thing here. And again, this thing for now depends on the gradient of the log of pk given 0. But what I can do is I'm just writing what is the expression of this thing. right? This is the scalar product between f, the gradient of log of pk given 0, integrated with respect to pk given 0. Now I use the identity that grad log of p is the grad of p divided by p. So this thing is in fact is just the gradient of pk given 0, right? Like there's nothing here. And then how do I go from here to here? I just use like the d-dimensional version of integration by part, and that is going to exchange my gradient into a divergence here. So I have a divergence operator here, and now I just have the integration with respect to pk given 0. So what does it mean? It means that when I look at the expectation of this thing here, that was depending of pk given 0, I can rewrite that in fact as minus the expectation of the divergence of f of xk given x0, and you see that the magic here is that it does not depend explicitly on the transition kernel of pk given 0. That's the main point of this derivation here. So the whole thing is that if I rewrite this stuff, it can be rewritten as the expectation of the norm square of f plus 2 times the divergence of f plus this term that I don't care about because it does not depend on f. But the neat thing now is that you see that this thing only depends on like how do I compute, what do I need to compute this stuff? What do I need to compute this stuff? Well, I just need to be able to sample from xk. And I don't even need to have access to grad log pk given 0. So now let's say, like for some reason, again, you are on a manifold or you decide to do some weird stuff. You know how to sample from xk, but you don't have access to this. You can use this loss function here. And this loss function is called implicit score matching. The other one was called denoising score matching for the reason I told you, that the fact that this is just a residual estimation. This one is called the denoising score. This one is called the implicit score matching, and it requires less information. So why don't we use that in practice? Any idea? Why don't we use that in practice in, let's say, in image processing? I'll give you a clue. It's in this term.
Divergence maybe?
Yeah.
Complicated?
Yeah. So because here, like, we need to compute the divergence in a very, very high. So this is an operator that goes from RD to RD, D being like extremely large, and we need to compute an estimator of the divergence, and computing divergence in very, very high dimension. What we usually do to compute derivative in machine learning, we use auto differentiation, and auto differentiation works very well if we have a function that goes from RD to R, and if you have a function that goes from RD to RD, this will require D times application of the auto differentiation, which is like something that is completely impossible to do. So what we do in practice is like we don't compute that exactly. We use some kind of estimator of the divergence, but yeah. So basically, we have some additional bias because this thing is quite complicated to compute in very, very high dimension. If you are in low dimension, this is perfectly fine. Yeah, but sometimes let's say if you work on a manifold, you can choose the function f so that the divergence is easy to compute or stuff like that. So that can be neat. Yeah, so that was just a small point aside to point you to the fact that there are ways to, like, what I've been showing you is one way of computing the denoising score match to compute this loss function, but there are others that exist out there. Yeah, so just before, what do I want to say? Backward sampling, yeah, okay. And again, like I just summarize here everything that I've shown you so far. We talked about that earlier, but we need to estimate. There was a question earlier about like, do we need to do that for every k? Yes, we need to do that for every k. So in fact, the loss function I showed you is just for one time step. We do that for all the time steps, and basically we aggregate all this loss function, and we make our neural approximator depend on k explicitly. So there is, I mean, I can tell you more about like what is the architecture of the neural network, blah, 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 but like just for like high level purposes, this is what we do. We just aggregate these things, and we usually put some kind of weight, and this is where like you have some kind of black magic about how to choose the weight here. But yeah, this is really what we do in practice for this kind of stuff. Here. Right. So again, the final thing was, you know, now that we have covered the training part, we assume that we have our trained neural network or our trained functional approximator, and now we need to sample. So when we sample, this is, you know, when you use Midjourney or DALL-E or, you know, this text-to-image stuff, you will put some text, and then you will wait a few seconds, and then you will get the image. When you wait a few seconds, what is happening is this. This is the part that is happening. You start from a Gaussian, and then you have these things that are being done in the background, where you kind of iteratively denoise the stuff with a neural network that has been trained before. The one thing so for those who are familiar with SD and their discretization, this thing here looks a lot like some kind of Euler-Maruyama discretization of some SDE, and it is. And so that's what we're going to see later. But there is a very good reason that I write it like this. It's because if you write everything in continuous time, in fact, what we are only doing, we are doing the discretization of some SDE. That's the only thing that we are doing. All right. Okay. So yeah, now I think like that's the end of my first introduction of the diffusion model, and my goal now is to present the link with the original derivation by Song and Herman, which was like kind of different in a way. Like the spirit was really different in what they were trying to do, and I think it gives us some kind of orthogonal and complementary point of view on all this stuff. So again, let's go back to let's rewind and remember what we are trying to do. We are trying to do generative modeling. We are trying to sample from P0. So if I had access to P0, well, if I had access to the grad log of P0, what I could do is I could just use the Langevin algorithm to sample from P0. So, by the way, is everyone aware of the Langevin algorithm, or do I need to do a recap on that? A small recap? Okay. So let's say now we are back in statistics. Let's say I want to sample from this. There is one algorithm that is called the unadjusted Langevin algorithm to sample from this thing. So what you can do is you start with x0 with whatever, like x0 equal x. You start with any point, and then what you're going to do is you're going to follow the following Markov chain. Plus square root 2, gamma, zk, zk. Right, so if you follow this Markov chain, what you will end up with is that if you look at the law of xk under under some condition on u, I could tell you more about what condition on u you need. What you will end up with is that this will converge to a distribution pi gamma, and pi gamma is close to P0 when k goes to infinity here. So why this is not P0 here is because you have a little bias because of the step size here. So basically you don't converge exactly to P0, you have like the small bias that is due to the step size. That's
When you know the bias, you can write it
Yeah. So if you satisfy the condition that is called strong convexity at infinity, so this is very weak. This is just saying that there exists R such that for all x, y, we have and so there exists. If you have this, and you also have that grad U is L Lipschitz. So if you have the Lipschitzness condition and this kind of strong convexity for x and y such that x minus y is greater than R. So that's just saying, like, outside of a ball, I have some kind of convexity. If you satisfy this condition, then you have that you can have that in Wasserstein 1 xk the distribution of xk and p0 is going to be less than c exponential minus r to the power k, with r which is between 0 and 1 plus gamma. I mean, like, there is some constant here, but this is what we call the geometric ergodicity. This means that we converge exponentially fast, and this is the bias that you have at the end. So this is true in Wasserstein 1, this is true in total variation, this is true in Kullback-Leiber divergence, this is true in whatever distance that you like. Although it might change the exponent here. Like, if you go to total variation, I think you only have, I think the best result is 1/2 or something like that. But yeah, like, you can control the bias, and all of this is explicit as well. The one thing I want to point out, because I used to work on that in my PhD. It took me 3 years to realize that. But, like, even though we say, oh, it converges very fast, it's exponential, actually you can compute that explicitly. And this thing is, yes, it's exponential, but it's so close to 1 that in practice it's very, if you have something that is very, very non-convex, it's something that is not doable. So it's nice to prove, like, theoretical result, but in practice this algorithm can get stuck in local minima very easily, because, I mean, let's say you have a mixture of Gaussian. What is this thing doing? If you forget about this part, this is just a normal gradient descent. So what it would do is, if you start here, your algorithm will go here, and then you have a little bit of noise, but it's attracted to this mode here, and then you're counting on the noise for, at some point, to kind of jump here and then move around here, and then move around here. So you can prove that these things happen, but it takes an awful long time to do. So that's actually one of the reasons why using Langevin for highly it's very hard to do sampling on like non-convex stuff here, because you have this kind of separated minima, and it's hard to jump from one point to the other. That's like one of the reasons why it's hard. So that's the Langevin algorithm. And you see that for the Langevin algorithm to work, you just need to have access to grad log of P0. So the idea of Song and Herman was that, okay, of course, again, I don't know P0, I only have access to sample, but what if I could just estimate the grad log of P0? Well, we can estimate that, right? Like, we can estimate it with exactly what I said before, with the implicit score matching. If I just have sample from x0, I just took my sample from x0, I have this loss function, I can minimize this thing, I will find something that is approximately the gradient of the log of P0, and then I can use my Langevin algorithm, and it's, if, fingers crossed, things will converge with my images of cats and dogs, and I can sell it to Google. So this doesn't work. This is kind of the naive approach, and it doesn't work. It doesn't work for two reasons. The first reason is what people call the slow mixing of the Langevin algorithm, and this is exactly the situation I described here, which is that the distribution that we are targeting is very complicated. And when we use the Langevin algorithm, if we use this type of thing, even if we had access to the perfect score, we would get stuck in local minima, and basically you would only sample one dog or one cat or whatever, and you will not explore the whole distribution. I mean, you will if you had an infinite amount of time. So that's one thing that is blocking us from using this thing in practice. The other thing is that I need to be able to estimate the gradient of the log of P0. And the problem with that is I need to estimate the gradient of the log of P0 everywhere, but I only have access to the gradient of the, when I use samples here, I'm going to use samples of images of cats and dogs, etc. And I will cover like the modes fairly well, like the modes of the cats, the modes of the dogs, etc. But like what happens in between, I have no samples from that. And so the estimation becomes extremely complicated just because like the coverage that I have is I don't cover the tails of my distribution basically. And so like when you compute this thing, the estimation becomes extremely complicated. The optimization becomes extremely complicated and you don't get like accurate score. So that was the two remarks that they started from this observation. They were like, okay, in an ideal world, we would be able to do this, but we can't. So how do we move away from that? And what they propose is to say, okay, there is this huge literature about annealing Langevin algorithm. So basically kind of changing the distribution that we are targeting slowly and starting from a distribution that is easier to target and then get to the true one that we want to target at the end. And that was their point of view, and you can see that how like this roughly relates to this kind of noising and denoising stuff that I was telling you about, because like we are kind of targeting intermediate distribution, and this is also what they were doing. So what they propose is that okay, what we can do is that instead of targeting P0, I'm not going to target P0 directly. I'm going to target a noisy version of P0. So instead of considering P0 in itself, the cats and dogs, I'm going to consider a noisy version. So this is the convolution operator. So this simply means that how to sample from this, I just take a sample of cats and then I just add noise. Right? They say, okay, I'm going to smooth the density by smoothing it with a Gaussian kernel. When I smooth everything with a Gaussian kernel, the problem of the estimation of the score goes away, because now, because I have added Gaussian noise, I just don't have the mode only, but I can cover my whole space because I have added noise here. So that was the main motivation, to kind of have a better, we are smoothing the distribution in a way, and by smoothing the distribution, we have like a better score estimation, but also by smoothing the distribution, if I let's say let's use this example here. If I do this and I smooth everything with a Gaussian kernel, I will have like something like this, okay? And when I have something like this, well, like even if I do gradient descent, it's much easier to bridge this energy gap here than to bridge this energy gap here. That was the main reason. So because like now, like these two modes are actually much closer together in terms of energy, and actually I will have like good exploration properties when I do this thing. So by adding noise, you kind of solve the two problems: one, the score estimation, and two, the slow mixing problem. Yeah, that was their main motivation. But of course, the problem is. The problem is that you are not sampling from the right distribution. So like you are not solving the problem that you want to solve. You're solving an easier problem. So either you have a hard problem, but you're sampling from the right thing, or you have an easy problem, but you're not sampling from the right thing. And so their point of view was like, okay, well, we're going to interpolate between that. We're gonna start by adding a lot of noise. And when we add a lot of noise, we have something that is easy to do. We're going to run the Langevin algorithm for this easy problem for a while. And then once we have this, we're going to reduce the noise level So that means that we are making the distribution more picked, and we are getting closer to what we want to do. And then we're going to rerun the Langevin algorithm for a while. Then we're going to reduce the variance and repeat that and repeat that and repeat that until we reach P0. And so this is exactly what they do. So this procedure of starting a Markov chain with the endpoint of the previous one is sometimes called the warm start. So like if you see that in the literature. But yeah, like the main goal like is, let's say you want to sample from this mixture of Gaussian, you start by sampling from this thing that is very, very spread out. This is easy to do. Sample for a while, reduce the noise level, sample for a while, reduce the noise level, etc., etc. Yeah.
And a silly question: how would you choose the sequence?
Yeah, that's a good question. So in their paper, they choose like some kind of geometric schedule. The schedule that they choose is actually related to the question of how to choose the step size in the previous thing I was showing. So this is like completely equivalent, like showing like how do I choose the sigma and how do I choose the step size. This is there is a one-to-one mapping between the two. This is actually like an open research question, like what is the best schedule to choose for this stuff. Basically, I think every paper that comes out like kind of choose either the default schedule that has been chosen by, let's say, OpenAI or whatever, or they come up with their own specific one. But there is no, like, let's say, very good theoretical understanding of what is the best schedule to choose. Usually what we try to do is, so to give you some intuition, is we say, okay, we can go fast here, so that means we can reduce, at the beginning we can reduce a lot, because at the beginning it's just sampling from a Gaussian. We don't need to spend an awful lot of time to sample from a Gaussian. That would be like wasting a lot of compute. And then we put a lot of sigma here. So that's why we have this kind of geometric schedule, because we want to spend a lot of time to be very, very precise near P0. There are like other possible choices based on like other consideration. But yeah, that's usually how we choose this type of stuff. At least in their paper, they choose it like to be geometric, and now like there are like other stuff going on.
Is it usually done data dependent, the schedule? So it would depend a lot on the measure I'm trying to.
Yeah. So what we usually do, and this is also explained in the paper I was referring to, the elucidating the design space of diffusion model. What you usually do is you take your data set and you renormalize your distribution to have mean 0, variance 1. And if everything is mean 0 and variance 1, then because the Gaussian, you assume that everything is only determined by the mean and the variance of your data set, which is not true, I agree, but like this is the assumption that we make. Based on that, like once you have renormalized everything, you can take the same schedule for every distribution that you have access to. But there is this kind of pre-processing step to renormalize your data set, to have a distribution that is more or less close to the Gaussian. Because you can show that like this process works well if this distribution is close to the Gaussian that you are targeting, basically. So the closer, because if this distribution was Gaussian, right, like that would be trivial. So like the closer this thing is close to the Gaussian, the better it is. So we try to make it as Gaussian as we can, and just by rescaling and centering. But of course that doesn't make it Gaussian, but like at least the first two moments can be fixed, and then we try our best. Yeah, that's the thing. There are some fancy stuff to do if you have access to the Fisher information of your distribution, but that will be another story. But basically, if you know the Fisher information, you can do more fancy stuff to rescale things, because not the Fisher information, the Stein information. So basically, the integral of the square norm of the Stein score. If you have access to this kind of stuff, then you can do more fancy stuff. Yeah. Other questions? Okay. So yeah, I mean, like this is just the algorithm that they use. So again, you choose the schedule of noise level here, like the schedule of the variance, and then you go from capital T to 1, so from the highest noise level to the smallest noise level, and for each noise level, you sample from the acetyl-Langevin thing, and you have estimated this score using the classical denoising score matching loss function that I showed you in the previous slide. So this estimation is exactly what I presented you before. We do the exact same thing, and then we have this kind of inner loop here. And you see that this is extremely similar to what I presented you earlier, and in fact, the only difference, like it will become clear when I move to the continuous setting. But when you move to the continuous setting, so I'm gonna try to, yeah, oh, that's perfect, okay. So if maybe you remember what I presented you earlier, I add an extra term. So I didn't have only the score, I also had like a plus xk. So it was gamma of xk plus the score. Let me try to bring it back. It was, yeah, I had something that looks like this before, right? So when I presented you the thing. So I had this thing here, I told you this is the discretization of some kind of SDE. And here, when you look at what they've done with Song and Herman, this is slightly different because you don't have this plus xk. But also, you know, what I presented you earlier, there is this kind of tiny difference where before, in what I presented you in the first part, I was targeting this Gaussian distribution that was like normal and with a covariance identity. Here, what they do is they just add noise, right? They don't rescale things. So if you think of like what is the forward noising process that they are doing? What is the forward thing? Like, you know, if you think of like if you keep like doing the annealing with like larger and larger noise, they are not targeting the Gaussian with mean 0 and covariance 1, covariance identity. What in fact they are targeting, you know, like they are targeting the Lebesgue measure in a sense, like they are the variance keep exploding for their stuff. So this is like, if you think of a term of SDE, in the first part I consider the Ornstein-Lebesgue process that I know is going to converge to the Gaussian distribution with covariance identity. Here, what they are in fact doing, they are considering a Brownian motion that has invariant measure the Lebesgue measure, so like it's, which they approximate with a Gaussian with very, very large variance. And when you look at the time reversal of these two processes, it changes slightly what is the discretization. So the difference in the discretization is just because of the type of forward process that we use. But like both of these processes are Gaussian processes, so we can compute exactly things in the same way. So like everything is still fine. But if you are confused because this expression is slightly different from the expression I showed you before, this is simply because this is a different choice of forward noising process. Then these two forward noising processes, they exist in the literature. So because in machine learning we like to reinvent the wheel, they have two, just if you read the literature, the one that corresponds to the Ornstein-Uhlenbeck process, they are called variance preserving. So these, if you read variance preserving SDE, that's the one I showed you in the first setting. Variance preserving being that like we assume that the data distribution at variance 1, and when we do the process I told you about, we can check that at every step the variance of our distribution is still equal to 1. So that's why we have the preserving here. If we rely only on the Brownian motion, this is what people sometimes call the variance exploding SD, because the variance explodes, right? But these two things again are like you have a one-to-one mapping to go between the two. It's not clear which one is best to use in practice. It's really dependent on the use case, like which neural network you're going to use, which schedule, etc. There are a lot of moving pieces here. But the important thing is that the principle behind these two things is the same thing. And the important thing is that for both of this stuff, like these are SDEs for which I have access to the transition densities because all of this is like Gaussian. That's the important part. Yeah.
Is it a numerical problem if you explode the variance?
Yes, I mean it should be, but so it's only a problem if what you pass as an input in the network has a variance that explodes. The thing here is that in the paper I mentioned before, they do like some rescaling before passing things into the neural network and rescaling of the output as well, so that everything has variance 1 basically. So they still manage to have things that are stable.
It's like a batch normalization.
No, it's not even that. It's just like I mean, it's kind of they do a bunch of stuff like that. There are like there are some. Where did I put my stuff? It's getting more. So they do stuff like this, but like when I say rescaling, it's really like instead of passing. So you have your functional approximation. If you were passing this thing, that would be bad because this has a very, very high variance. So what they only do is something like rescaling by the sigma, and the sigma we know what it is because we can compute it explicitly. And then they also rescale, like there is so they have like C, they call that C output, C input, and they compute that for like everything, and then they also compute the weight, etc. But like yeah, this is like just very simple analytic stuff that they put. I mean, this thing is nasty in terms of like batch normalization, layer norm, etc. There is no batch normalization, but like there are some normalization going on. But yeah, when I say normalization, it's just normalization of the input and output. Yeah, I think that's good. Okay, so is there any question on that? So what I presented you again was just the original idea from Song and Herman. So that was in 2019, and then early 2020. They realized that, oh, actually all of this, if I go into continuous time, that corresponds to the time reversal, and they actually derived like everything that I told you with the VPSD, VESD, and this kind of general framework. But this should at least guide you through the original paper. And yeah, that's I think that it also gives a motivation in terms of like more statistical stuff in terms of like the what is actually going on. Yeah.
You called it the neo-Langevin dynamics, so I guess there's a huge literature before that on this. So is there new insight in this paper, or they just apply it to? It's
quite different from the usual literature on Anil Langevin. So if you're usually what we mean by Anil Langevin is there are multiple ways of doing the annealing. So that's I think that's actually a very quite deep question. But so there is one way to do right now the way we do the annealing is so this is something like that we do. If you look at the Anil Langevin literature, when people talk about annealing, they don't talk about that. They talk about so basically let's assume again that P of X can be written as this. When we talk about annealing, people usually refer to something like that, which is different, right? Like you're here you're convolving your density, and here you're rescaling the steps. It has these two things have very similar effects, but they are quite different. And the schemes that people have analyzed is more like this type of stuff, and not so much this thing. So really, I have 5 minutes, so maybe I can talk a little bit about that because I think this is actually quite important. The difference between these two things is there is this really, I think it's Filippo Sant'Ambrogio, who wrote this book on one of the books on optimal transport. I forgot the name. He makes the point of differentiating between when we do statistics and probability in a vertical manner or like horizontal manner. So what he means by vertical is that vertical roughly means that you are modifying the density, because what I mean by vertical is that if I use this kind of thing, this is like, this is just trying to make this to flatten this thing by just like pumping this down by making the sigma large. So what I'm effectively doing is I'm looking at my graph, and then I'm pushing I'm pushing things down and this up to make it smoother. When we do this, we usually when we work in this vertical manner, what we usually think that we have access to is this type of quantity, right? Like here, I'm really leveraging the fact that I have access to some kind of energy. So this thing is like super useful if you have access to energies and if you are in the context of statistical physics or statistics. Now, when you do this type of stuff, you don't move the mass you don't really move the mass like up or down. What you are doing is like this kind of average. So that's why he calls that horizontal, in the sense that I'm just going to spread the mass like this, right? Like in a horizontal manner. And when you do this stuff, you see that I completely lose the fact that before I had access to the explicit density of this stuff. Here, I don't have access to the explicit density of this stuff because this is a nasty convolution with a Gaussian. But sampling from this thing is much easier because this thing is just adding noise. So when you deal with like densities, it's smarter to deal with like this vertical stuff. And that's why I think it was studied before, because in statistics and statistical physics, we usually assume that we have the energy. But now if we move to the realm of machine learning, we have access to samples where we don't care so much about the density. So we are perfectly fine with doing annealing in this type of way, but we care about the samples and we want to do simple operation on the samples, and this corresponds to something that is very simple on the sample. So there is really this kind of distinction between vertical, I mean, for me, at least, I try to think about it in terms of like what I do in vertical manner and horizontal manner. And I think this is kind of a useful analogy as well to think of like what works, to gain some kind of intuition of what is going to work and what is not going to work. Because like, again, to go back to what you were saying earlier, you know, like you were talking about estimating ratios of densities and stuff like that. For me, when I think about estimating ratios of density, this is something that is kind of like in the realm of like vertical probability, where I'm going to have to estimate, like compare stuff like point-wise and like try to estimate, okay, how much do I need to multiply to get to the thing? Whereas when I need to estimate the score, this is like how much do I need to move in my space to like move the samples. And I think this is, I don't know, at least for me, it was kind of illuminating to try to think of these two things, and that the two things are like completely valid, but like if you have access to samples, this thing is better. If you have access to a density, this thing is better. And then the funny part is that when you have access, like when you have like mixed information between the two, like then what do you do? Like you need to have some kind of a mix between these two things, but like that's kind of like open research problem.
Can be mixed information, you can have both, or?
Yeah. So both, for example, there are cases where if you work on protein design, sometimes they have like they have an energy that is given by molecular dynamics, but it's like really, really hard to sample from that. And because they also have like a wet lab experiments, they also have access to samples. So in a way, they are in this kind of best of both worlds situation, except that the distributions are extremely complicated to sample from. But now you can kind of leverage, you can try to somehow like leverage these two things together. I mean, that's the one example I can think of where you have access to both information. If you have access to zero information, I don't know what to do. That's just
it's like in pins when you have some data, access to some data, and also to PD.
Yeah, exactly. It's exactly the same stuff. Yeah. I mean, I would think of it in exactly the same way. Yeah. Okay, I don't think I have time. Yeah, maybe it's better to. Yeah, like in 3 minutes, that's not gonna do it. But like, I think we can stop here probably, and then I'll go back with the implementation details later. Hi, everyone. We're back. So, wait, what time is it? So it's 1:30, and we stop at 4. I guess we have a small break in the middle.
Small break.
Yeah.
Then we also have coffee for the rest of the crew. Yeah.
So like we do 1 hour, 1.5 hours now? Okay, cool. Okay, so before I go back to my stuff, is there any question from this morning? Like something like maybe lunch, you know, like open your brain to something, no? No, all good? Okay, yeah, again, don't hesitate to interrupt me. So now like so far we've seen some kind of introduction to diffusion model with our stochastic calculus, where I showed you the forward, the backward, etc., the Tweedy identity to estimate the score. We plug that back into the denoising process, and it works. I showed you the connection with the original paper by Song and Herman, and like the link with Anil Langevin. So what I hope to do this afternoon is I'm going to spend a little bit of time, especially for those of you who are, I don't know, more on the practical side or would like to know really how the things are done for, like, in terms of the nitty-gritty details. I want to spend a little bit of time of like what are the common tricks that are used to make these things work and scale. So yeah, I'll spend, I don't know, hopefully not too much time on that, but I think it's important. Then I like to point out some links with VAE, so variational encoder. That everyone here has heard about variational encoder. You can say no if that's okay. Okay, well, I'll take it like I won't make a general introduction to variational encoder, but like there will be like some stuff that is shared. So yeah, hopefully it will be clear. Why I think it's important is because a lot of the papers are based on this interpretation of diffusion model. So the original paper that was doing the link with variational encoder was called DDPM, so Denoising Diffusion Probabilistic Model by Jonathan O and co-authors in 2020. I mean, everything is equivalent at the end of the day, everything is the same thing, but like it gives yet another perspective on diffusion model, which I think can be useful. And then hopefully, but like, yeah, this is only hopefully, if we have time, I'll move to the continuous time and talk about like time reversal of SDEs, which is, I think, the most beautiful interpretation of these models. Right, all good? Right, so implementation details. So what I've showed you so far, like the loss function, the sampling scheme, everything that I've presented, I have not hidden, you know, something very crucial to you. Like really what I've presented to you is really what is implemented in practice, except for a few tricks that make things like work better, which some of them are important, some of them are not so important, but I would like to highlight which ones are like really key and like maybe it can help also understand a little bit better the loss function. So if you look at the 2019 papers, the images were, there was an image model papers, like they were trying to do like Celeb A, Cypher 10, MNIST, you know, if you're familiar with these data sets, they are trying to do this in the Song and Herman paper. And they were saying that the models were hard to train. So basically, their approach was they noticed that there were like some training instabilities and sometimes the model was diverging and it seemed to be a bit tricky to train. And then like in the last 2 years or more, there have been like a bunch of new tricks which have really greatly improved our understanding on how we should train this type of stuff. So here again, I'm switching to like now my family of approximators are neural network. And this is what I'm not going to discuss the architecture here in detail, just to give you some pointer, I won't dive into this. The most common, until 1 month ago or 3 weeks ago, the most common architecture to train this stuff was called the UNet architecture. The UNet architecture is a special type of neural network that was specially done for denoising task, which is, you know, I showed you that the loss function that we have is a denoising loss function, so it made sense to use this UNet type of architecture. Just to briefly summarize how it works, it consists of like different blocks of your neural network and how they interact with each other. Again, I'm not giving you like the full justification of why, but basically you have like convolutional layer here, convolutional layer followed by some kind of self-attention and some kind of layer normalization. So this will be like one block. Then like the latent representation are passed to another block and yet to another block, then to another block here, then it goes up. So basically here, like you reduce the dimension. Every time you do this, you reduce the dimension. You arrive at the bottom of the UNet and then you go up again. And you have what we call skip connection that share the latent variable. The reason for that is for training purposes. So this is, again, like kind of like going into the nitty-gritty details here. There is a part about the time embedding. So the fact that, you know, we need to input not only X into the network, but we also need to input K. The way we input K is like shared with all the neural network architecture, and this is done with cosine and sine embedding the same way it's done in transformers. So like I'm just, if you are familiar with this stuff, this is just to give you some idea. Very recently, there has been like other approaches that are concurrent to UNet that seem to work extremely well, which is called VIT. So this is a visual transformers, and basically this is instead of relying on like convolution layer and self-attention, what you just do, you take your image, you take patches of the image, you consider that as like tokens, as you would do in a language model. You have your tokens, and then you apply a transformer architecture, and that's it. And this thing is notably used if you've seen this actually really amazing diffusion model for video by OpenAI that is called Sora. One of the main difference and main improvement they said compared to the rest of the architecture, compared to the rest of the diffusion model, is their use of this stuff, which is known to be like very, very, very scalable, and people have worked a lot on the engineering side to make it work. So yeah, so these are like, I think, the main two common architecture that are used for this type of thing. But again, I won't dive into that except if there are like specific questions for this. Instead of going, I'm going to talk more about like how do we modify the, how do we use like what kind of knobs we can turn into the model to make it better. The first one I want to discuss is, you know, I told you when if you remember what I had before, I put a fixed step size. So basically I said, okay, we noise, and I told you about like a noising process that was depending on some step size gamma. Well, gamma was, you could interpret that as the discretization of some kind of SDE, and I took it fixed. And I never discussed why I should take this fixed or not. Actually, in practice, you should not take it fixed. The reason for that is because if you look at images, the way you destroy the information is that the high frequency are very sensitive to the noise. So as soon as I add a little bit of noise, you know, like the hair or like the small details are going to be immediately destroyed with the addition of noise. So if you add noise too quickly, then you destroy a lot of structure, and that means that your diffusion model is going to spend a lot of time on the low frequency, and then in the last few steps, it has to fill up all the gaps to make something that is like very, very detailed. So usually what we do is, and like the global intuition is that we need to have more step size near the data distribution, and we're fine near the Gaussian, because we can take large step when we are near a Gaussian distribution. It's okay. So the kind of scheme that we use, sorry, the kind of scheme that usually people are going to use. So this is the discretization. Like this is an example of the discretization of the time. So you put a very small step size near the data, and then you increase it, like usually with some kind of linear type of schedule. So you have linear schedule. You also have like things that are based on like a cosine function to interpolate between two values of gamma min and gamma max, stuff like that. But this thing is called the schedule, and there is actually like a lot of ongoing research of like what is the best schedule that we should choose for a diffusion model. It's not clear at all what is the best one. It's also application dependent. So if you're doing protein, maybe this is not the thing, you know, does the analogy with high frequency and low frequency still works? If you're doing with text, like maybe, you know, what is a high frequency in text, that's not clear. So this thing is like very specific to the type of media, like image, video, whatever, where you can deal with like frequency and we have some kind of intuition. But it turned out to be like really, really important to design this type of schedule to have things that scale and give like good result and like very detailed result with like very high resolution. So yeah, that's one thing that is quite important. And when you read a paper that discusses the schedule, what we are discussing really is this type of discretization. So something I should say is that usually they don't talk explicitly about the discretization. They say that, I know I haven't talked about that, but like as I was saying that this is the discretization of an SDE, usually what they say is that they say that they are going to change the speed of the time in the SDE, and they always consider a discretization that is uniform. But like there is a one-to-one mapping between changing the discretization, right, and changing the speed of the SDE, and then choosing a uniform discretization. So these are just two sides of the same coin. Here I'm just, because I haven't talked about the discretization of SDE yet, I'm just saying like you choose a different step size. That's thing number one that is quite important. Thing number two that is quite important as well is how we weight. Yeah, I told you, you know, like we have this denoising score matching loss, which is just the denoising loss at all time steps. And we just aggregate them into one big loss function, and then we put some weight here. The problem is that if we put 1 here, if you look at the variance of this loss, the variance of the loss is like very different, far away from the data and close to the data. And this is something that can be seen if you look at what is the target. So the target thing, the thing that I'm targeting here is this thing. And I told you it was just the noise rescaled by the variance, right? So the thing is, when you are close to the data, sigma is very, very small, all right? So because I haven't added a lot of noise. So the variance of this thing actually is going to be huge because I'm divided by sigma. So near the data, the variance is large. Away from the data, the variance is small. And so this is something that can be like kind of hard for the network to understand because the network has to somehow learn that like, okay, like the thing I'm targeting away from the data has like low variance and near the data it has high variance, and we'd prefer to have something that has, you know, the same variance all the time. So to stabilize the learning and to stabilize the training procedure, we usually put some kind of weighting here. The weighting is chosen so that like approximately everything is well behaved. Again, like this is just like numerical consideration when we do the training, but it turns out to be quite important to stabilize stuff. So the paper I was mentioning before, like elucidating the design space of diffusion model, Appendix B6 does that. So they discuss not only the weighting, but they discuss also like, again, the input, how you should scale the input, how you should scale the output, yeah, all this type of stuff. So yeah, like there are, when you go to the SDE point of view and you mess around with like some Girzanov theory, you can justify some kind of weight here that you should put, but this is usually not the one that is used in practice. But it's fine because like all the different weights that you put give you the same solution. It's just that if you were to compute like elbow, so evidence lower bound, there is one preferred weight, but like we don't really care about that. Yeah, so this thing, like as I was saying, changing the schedule and changing the weights is quite important. The ingredient number 2. And something that I think might be like one of the most, probably the thing that made this thing, like one of the most important thing is this exponential moving average. So, you know, like when you train a neural network, you use any kind of optimization algorithm that you like, let's say SGD or ADAM, and you update the weights, right? You update the weights, you sample your batch, you compute your loss function, take the gradient, update. The problem with that is that because even if you fix the variance of the loss, you still have, because the way you sample the batch, you might have like, the loss function might sometimes take a very, very high value and sometimes a smaller value, which makes the gradient to be like quite spiky. And it's not, when you look at the training of a diffusion model, if you just look at the weights of the neural network, they are like kind of oscillating and you're like, oh, wow, what's going on? But this is perfectly normal. It's because like there is a lot of stochasticity because you are trying to in fact optimize a lot of objectives at the same time. The thing, however, like the fact that the weights are kind of, the evolution of the weights is kind of spiky, makes it like a little bit hard for the model to learn things correctly. so what we do in practice is that we have the weights here, the weight theta n, so the weights of the network, which are updated in the classical way. So we keep track of this sequence, right? But we also keep track of a sequence that is an exponential moving average of this weight, right? And which is just given by this. So you kind of smooth the sequence of weights, okay? And what you consider at the end when you're going to do the sampling, so when you're going to do the sampling, you're not going to use the weight theta n, you're going to use the weight theta bar n. And this is actually really, really important to stabilize things. So one of the main reasons the paper of Song and Hermon in 2019 was not working extremely well, was because of that. So this is what they report here. So I don't know if you can see really, but like this thing here, this is the fit score, which is kind of a metric that we use in image processing to say if the image is good looking or not. And in blue, this is if they use only theta n, and this thing here is during the training, like if they look at what happens during the training time. So if they just use these weights, you see that like the quality of the images like during the training like oscillates a lot, and this is again due to the instabilities of the learning. If you use this kind of EMA stuff, the exponential moving average, you get curves that are like much smoother and usually lower. So like for example here, like you can see that like the difference is actually quite huge. So yeah, this thing very, very important. That's the kind of like one of the few tricks that I wanted to mention. And the one, sorry, when am I going to talk about that? Yeah. So there is like just two other tricks that I really want to talk about, and then I'll make some kind of summary of this type of tricks. The one that I really want to talk about is, I will dive into this later, but again, I said that all of this, whatever we are doing here, this is the discretization of some type of SDE. And actually the discretization that we're looking at is a very naive discretization. It's called the Euler-Maruyama discretization. So if you're familiar with ODE, this is the stochastic equivalent of just the Euler discretization. And we know that we have much more precise scheme that we can use instead of the Euler scheme. In particular, you could do like some kind of exponential integrator. You could do like some kind of extrapolation scheme and stuff like that. So there is now, I mean, I didn't even attempt to list them, but there is a huge literature on what kind of sampler you could use here. So that means that modifying this step here in a smart way to fit better to the underlying continuous dynamic. Like you have an underlying continuous dynamic. I'm trying to fit to this dynamic to the best I can, and this thing is a legit choice, but it might not be the best choice. And so there are a bunch of stuff here. So here I talk a little bit about the modified Euler-Maruyama scheme, which is a way to modify the variance. But I mean, we don't even need to really dive into the detail here. The important thing that I want to point out is this is another avenue to modify your sampling scheme, which is to modify the discretization and the way you sample from this autoregressive model here, right? So what I was talking about before, so modifying the discretization, modifying the weights, and modifying like doing the moving average, that was like during the training, okay? That was like when we trained the model to have like a good score approximation. Here, like there is no training involved. Here, this is just about like what we do at sampling time, and at sampling time we just follow this, and we can change this stuff. Right? That's all I'm saying here. Again, like if you have any question, I can dive into the details, but like this is just to highlight the possible like avenues of improvement for this type of model. Right. And the last thing I want to mention, which I think is something that is actually quite important, is, you know, I told you from the beginning, I don't know if you've played around with these models, or like if you played with DALL-E, Midjourney, or like ImageN, you know, like all this text-to-image model. So for those of you who don't know, the way the way these models work, like that's either will it be for like text to image or like text to video or text to audio, is usually you will have a prompt, let's say, I don't know, image of a stray cat. And then the diffusion model will give you an image of the stray cat, right? Like this is, so far I've just said, okay, I want to sample from my distribution, but I've never like imposed any condition on which part of the distribution I was sampling. I said I sample from cats and dogs, but like how do I sample from cat and dog? So there are multiple ways of introducing conditional sampling into diffusion model. One very, very simple way of doing that is, let's say that now your data set is not only x0 I, so it's not, before I was just saying, okay, these are like images of cats and dogs, but now like you have an annotated data set. So you have this, and you also have like some text that is telling you, oh, this is like an image of a cat, this is an image of a dog, etc. So it can be text, it can be label, it can be whatever you want. It's just a condition that is associated with x0. Then what you do is you do exactly like the whole thing that I've said before remains the same. The only thing that you change in the loss function is that now your f, it takes as input k, it will still take the time as input, it will still take xk as an input, but it will also take c, so your condition basically. So you train a model, and here like this is the same thing as before, log p k xk x0 blah blah blah, this thing. So now when you sample, that means that now when you sample, you're gonna start from a Gaussian, and you're gonna start, so you train the model this way, right? And I can do it because when I have sample, I have a sample here, and I also have the associated prompt, so that everything is fine. Like all of this can still be computed. But now when I want to sample an image of a stray cat, I just do the same thing as before, and I just pass the prompt here to the model. And that's really literally the only difference that we do during the training of these models. There is one trick that we do, is that sometimes we also train, when we do this thing, we train the model in a conditional way, right? Like we don't learn P anymore, we learn P given the condition. We found it, it's also valuable to learn the general model without any conditioning. So what we do during the training is that sometimes we use the prompt, and sometimes we pass like a dummy prompt, which is like void. So in that way, we are learning to model both this distribution, but also the unconditional distribution. Because if we don't pass the prompt, then there is no information about the condition. Yeah.
Yeah, but to me it's not obvious. I mean, how you integrate this condition in the function when you learn it.
You mean how do you put it in the neural network?
Yeah, for example, or
So for text to image, like if I go back to this, if I go back to the unit here, all the conditioning here, like I have conditioning on time, you also add the conditioning here. So for example, for text, what you will do, you will take a text pre-trained text embedding, let's say clip, or like whatever, usually it's clip. Well, I don't know now, but anyway, something like clip, and then you just concatenate this representation here, and then you pass it like this. But it can be with text, it can be with class. Let's say if you have the, if instead of having just text, you have like class of cat, dogs, tree, plane, stuff like that. This also works. Like this works like for a generic condition, but this is usually when people talk about text to image model, text to video model, which is like kind of what is all the buzz these days. This is really how they train the model. So like with that, I'm giving you like really the recipe to train this kind of conditional model. The one thing that people, yeah.
Like, how do you handle the fact that the inputs will not be exactly like the labels? Like, you need some kind of modeling also in the language part, right? Because,
Yeah.
for example, in your example, you wrote image of a stray cat, but probably the labeling is just cat, stray.
So that's why, I mean, if you use just labels, then that's fine because like the label is just, depend on the data set. Let's say you're using Sci-Far 10. You have 10 classes and then it's just a number, right? You just pass another number. So you cannot ask for a stray cat. You can ask for cat, dog, horse. I forgot the 10 classes, but you get the idea. Now, if you use text here, you're right that you really need a good embedding and a good representation of the text. And so usually this is done like, let's say you have trained a language model. The language model will learn some kind of embedding, and this is this embedding that you use. So there is some magic happening here about how we choose the embedding, but like this is like kind of like NLP type stuff. Like we usually don't mess around with it, and we just take something that is pre-trained that is giving us like something that we think is a good internal representation of sentences. Yeah, that's kind of a bit of black magic happen here. Yeah. Any other question? Right. So, yeah. So that's I think the main thing like that I wanted to point out is that whenever you have this image that look good and for the point is that like for generative modeling, usually you don't have a lot of control because you're just sampling from the distribution. You can put control back into your system by considering this type of loss function, which is a very simple modification. Something I'm not talking about is that there are many ways to modify the sampling scheme in order to leverage even further the fact that you have access to this extra information. Because right now I'm using it in kind of a dummy way by just putting that in the neural network, but you could think of like more of like smarter ways of doing so. And again, something I'm not going to discuss into too many details, but that is used a lot, is called classifier guidance. And classifier guidance basically will work in a way that you're going to use, let's say you want to sample from the class C, instead of using just the score in the sampling scheme, instead of using the score with C here, right? You're going to do the following. So I don't have time to go into the theoretical explanation, theoretical explanation of why we do that, but I want to show it to you just so you are aware of it. So right now I say, okay, when I do my denoising, I do something like that, right? Like this is supposed to ensure that I will sample from the class C. Okay, like I'm just going to simplify a little bit. Like this is xk plus 1. I'm forgetting the time just because it's a bit long to write, but right, and you have something like this. Right? So this is the simple modification that allows us to sample from the conditional distribution. What people do in practice is that we're going to replace that by something of the following form. So we are replacing the score here by 1 plus, I'm going to call that kappa. Well, kappa is some number. 1 plus kappa, the score, xk plus 1 cc, minus kappa s theta xk plus 1 c, and here the thing but evaluated at the empty class thing. So, okay, what does this thing do? So again, I'm replacing this thing by something like that. And here kappa is is a positive number. So what is the effect of this stuff? The effect of this stuff is that I'm boosting this gradient here. Instead of having a factor 1, I have a factor 1 plus kappa. So you can think of it as like pushing in the direction of like the conditional distribution. So here, if C was dog, I am pushing in the direction of dogs. And with this minus kappa here, I am pushing away from everything else. So because this thing is the rest of like, this thing is like the global unconditional generative model. So the effect of this stuff is to concentrate towards toward the class.
And is there any theoretical?
Yes, so there is something that tells us that this thing is not exact, and like this is not going to converge to something that is tractable, but you can somehow modify it with like some kind of sequential Monte Carlo procedure actually to show that it converged towards some kind of how do you say annealed version of the conditional distribution. So the effect of this usually you play around with the kappa. If kappa is very large, you are very well centered around your class. So what will happen is that, let's say you want to sample from the class of husky dogs, you will always have like one image of husky. Like it will be like too concentrated, but it will be a very good image of husky dogs.
So you have a compromise between diversity and this. How do you tune it?
So that's an excellent question. So basically, yeah. So then the point is like if this is very high, you have good fidelity, low diversity. If kappa is low, you have high diversity, low fidelity, and then it's kind of like one hyperparameter that people tune. But this is something that is actually super important to tune. And a lot of this, there is. I just want to touch a word on that because I'm glad that no one asked the question so far, but like usually sometimes someone, when I present this stuff and say we only learn from samples, there is the question, but like how can we learn to generalize, right? Because we are learning from a data set and somehow we are supposed to create entirely new images of cats and dogs. So it seems like completely nuts. And somehow it kind of works. Like we can show that we create images that are not in the training data set. Like you can actually look at what are the closest point in the data set and you see that like, okay, do you have like stuff that of course like like do you have like patches that you can recognize from like other images, but this is not a point that is in the training data set. So for me, like my current interpretation is that all of this is because of the architecture of the neural network that somehow learn to interpolate between this sample in a somewhat meaningful way. This is a very broad statement, so like I'm not putting too much money on that, but like there is really something happening because of course we know if you had a training data set like the grad log of PK, if I had like let's say 10 samples, I know what the grad log of PK should be. Because PK would be a mixture of Gaussian. I could just model the thing with this grad log of a mixture of Gaussian, and then I will fall back to my training data set. So the fact that we are able to generalize is because there is something happening with our functional approximation that is not like exactly the score of the empirical measure, but somehow is a somewhat good approximation of the underlying measure that we are trying to model. So. But there is this problem that if we have something that is way too expressive and a very small data set, we completely overfit to the training data set, and then you have like huge memorization issues. And I don't know if you're aware of like Getty Image like suing like OpenAI for DALL-E because you can see the watermark. Like you can generate images where you see the watermark of like images that are supposed to be like copyright protected. But apparently have been used in the training data set of these images. And that is a very good example of like how these models can memorize. And it's really hard to characterize how they memorize and when they memorize and how we can avoid this memorization issue. So basically that means that sometimes the model can collapse some example of the training data set, that will depend a lot on how you curate the training data set. Let's say, for example, if you have multiple examples of the same image in the training data set, you're putting a lot of mass on like one image, and this is how you can end up with something that will collapse. Or in the case of text to image, if you put a very, very specific prompt, what you are in fact doing is like if you put a prompt, let's say a picture, I don't know, I have no idea like this, but like if you put a very specific prompt, you are basically removing a lot of the mass from the distribution that you are targeting, and in fact are just restraining yourself to learn on a few samples, and then in that case you can see memorization arising. And that's one of the, this is not specific to diffusion model, this is a main problem in machine learning and from the statement of the problem of generative modeling. So far, this is still a very gray area in terms of like jurisdiction, like how do we deal with this stuff? I was at ICML last year, and they had like the very interesting panel on like people who actually are lawyers, the people like arguing for and against OpenAI and technical people, and it's a very hard challenge. Like how do you do mathematical theory of copyright infringement and like what is intellectual property, and it's extremely hard to quantify this stuff. Anyway, I find it like quite fascinating how we could think of better ways of avoiding memorization, but just characterizing memorization is hard. And why I'm talking about that right now is when we do this stuff, the classifier guidance that is used in all of these image models and video models, they all use classifier guidance with very large value of kappa. And when you use that with a very large value of kappa, you're reducing the diversity and you're actually increasing the memorization. So one big challenge for a lot of big companies is to manage to still capture good fidelity. So we want to use kappa large, but also we don't want to be sued. So we want to still avoid the memorization. And this is, I think, like, this is still this is still a challenge for a lot of, for all of these models here. So yeah, that's something like I think, everyone should be aware of, that like there is nothing like magical happening here. We only learn from the data, so like at some point there is something happening with the data. It's not like we are there is no like external signal that tells us, okay, we have learned the underlying distribution of cats and dogs, etc. If we can generalize somehow, I think like is that because we managed to have some kind of good internal representation and good interpolation properties with the neural network. But yeah, there's just a like small caveat for all of these models. And it's also, you can avoid that if you have huge data sets, but let's say, for example, in protein modeling, the data sets are usually smaller. And in that case, you can really see that sometimes some structures are really easily repeated, and like you can fall back to, the model can collapse to memorizing the training data set quite easily if you're not careful. So yeah, be careful. Yeah.
I think I'm missing something on the metrics. So if you say you compare images with the ones generated with the ones in the data set, and you see that the generated image is quite different from the ones in the data set, how do you measure the distance of these in the latent space? Or
so there are many ways of doing that. So like sometimes, usually you look at a bunch of different metrics for doing this. So you can use the L2 distance. That's usually not that good. Or otherwise, sometimes you use LPIPs, which is I forgot the name for what it is, but like it's basically going. You pass both images in the neural network, look at the feature, and compare the feature. So yeah, just some kind of latent space thing to compare. And yeah, also. Hello. Yeah. Something that something that is done is also sometimes to just look, like just go through the whole data set and like pay people to look at the image and like see which one is the most similar. Because like for the human eye, that's still the best metric that we have.
And if you say something like even the closest images look different, then you use the latent space to compare them, and then you look with the eye that they're different as the actual image.
Yeah. I mean, like usually you have like some. When I say that, like there have been like quite on memorization, there have been like quite thorough study on like comparing how the latent representation is correlated to the visual inspection. Usually, it's a good indicator. It's not perfect, but it gives you like a good intuition of what is happening. And you can see, let's say, like the first 20 examples in the training data set that are the closest. And like there are clearly examples for which you are not in that area. You will recover, like, of course, you will recover like part of the faces. You can maybe see that in another image and stuff like that. But like it will be like a truly new image. Yeah. So this thing is learning some kind of. I don't know if I like to say that, but it's learning some kind of concept of like the image. It's learning like at least how to match things together and like, okay, so if I want an astronaut, I should take the image of blah blah blah, like put it on the moon, etc. Like it's there is some kind of there is something happening here, but it's it can also completely regurgitate like some training data sets. That's just what I'm saying. Yeah.
So I don't know if maybe this is a sensible question, but like so you have the net structure, right? Which is going up, then down, and then up again. If I
down, then up.
So, sorry, yeah. So, but it's going down in dimension.
Yeah.
To some extent, right? So, but then when I think about the noising process, this is like kind of uniform in terms of the size, right? I have my image, and then I just noise
Yeah.
repeatedly. But then I would expect some kind of, at least intuitively, cats is a low-dimensional manifold of images. So just assuming that I need all this space seems very wasteful, right? Like I have a very high-dimensional Gaussian noise, but cats are just 4 legs and a nice face, whiskers and stuff. So I should go down as I noise.
Yeah.
I should put all of these things together to say, well, the manifold is very small. I want the uniform measure over the cat manifold, not over the image manifold, and then refine iteratively to some extent. Like pull all the dimensions down that are not cats.
So, I mean, like one way of people are dealing with that is that in all of this model, you're not usually directly working on the image space, you go to latent space. So you learn some kind of VAE that is going to reduce the dimension, and then you do the diffusion model in the latent representation. So that way you reduce the dimension. You don't reduce it by that much, actually, because you need the VAE to be quite good at restoring the image. So you still keep a lot of dimension, but still you reduce the dimension, then you do a diffusion model into that space. And but you don't change the architecture of the unit here. That's what I'm saying.
No, but then in that case, like, we're not doing all of that at the same time, right? We're going down in dimensions supposedly that we can kind of compress the concept of a cat and then we noise the concept of a cat onto uniform.
Yeah.
So I was thinking more, is there something that does all of these like at the same time? So we noise, we go down, we noise, we go down, because we should.
Okay. Yes. Oh, okay. That's a good point. Yeah. So that's one thing about diffusion model is that one key assumption that I have and that I think is common to all of these models is that the target distribution, whether it be Gaussian, uniform, or like the Lebesgue measure, whatever, needs to have the same dimension as the distribution I'm targeting. And when I say the same dimension, is the same, like, no, it's not the intrinsic dimension, right? Like it's if I'm defining stuff on the space of images, I need my distribution to be in the same dimension. So that's why we are targeting Gaussians which have the same, which are like super high dimensional, even though we know that the implicit dimension, the intrinsic dimension of the cats and dogs is like much smaller. It's quite the challenge to, we've tried that, it works, but it's not perfect. It works, but like, I mean, there's a lot of improvement to be done. To do what you're saying, which is, okay, we noise and we also reduce the dimension at the same time. The problem with that is that then we kind of, it amounts to kind of defining a new noising process where not only we noise, but we also drop randomly dimension. So now you move, instead of having SDE, in fact, you have jump SD, where you can like, you define a kill state and then you just kill things. And then you can also do time reversal of jump SDs things become a little bit more tedious because when in the denoising process you need to add dimension back, and you can do it, you can write everything, but like defining how when we add the new information, how to add it conditionally to the rest of the information, the update is quite complicated to have, and it's not really, it's tractable, but like the learning is difficult and it's hard to do that while learning the score as well. So I think it's still an open problem how to do that like efficiently, but you can definitely do that. Like that was one of the intuition behind behind like we proposed something like that for protein modeling actually, for like, because sometimes you don't know how much amino acids you have, and so you would like to keep that as random as well, and that involves like dropping dimensions. But yeah, I mean like this is an open problem, I think, like what you're describing here. So, but an interesting question, yeah. Other question? No? Okay, so yeah, sorry, I spent a little bit too much time on that, but just to kind of conclude on like the implementation details, the one thing I want to emphasize is that normal training, like naive training of this model works, but it's kind of unstable. There are ways to stabilize it with EMA, with weighting the loss function. Again, a lot of these tricks are described in the Elucidating the Design Space of Diffusion model paper. There are also ways of changing the sampling. Most of it is like informed by the structure of the underlying SD that we are looking at. And if you want to do things that are conditional, there are a bunch of other tricks that I cannot. I mean, I don't have the time to talk about. But the main one being like classifier-free guidance. Or classifier-free guidance, depending, like sometimes it's called. But be careful that when you scale all this stuff and when you use some of these tricks, sometimes there is the caveat that the model will start to memorize, and this is a big problem. Right. Okay. So that was the main point I wanted to convey. Yeah, so if that's okay, now I'll switch to the link with VAE. So this thing here, my main point here is to show that this thing was introduced completely independently of the paper of Song and Herman. The two approaches are quite different. You still recover the same thing at the end, but if you are more familiar with like how to optimize the log likelihood, etc., I think this thing will appeal to you a little bit more. Okay, so I'll try to do that, and then we'll dive into the real thing with the time reversal. Right. So yeah, I don't care about that. I'm gonna dive directly into this. Okay, so yep. Right. Okay. So here, like, is there like any? Should I do a recap on variational enzo encoder, like a 10-minute recap? Yes, I see some yes. Okay. So VAE, or variational enzo encoder. So how do they work? This is also an algorithm for generative modeling that was proposed, well, a while ago. And the goal here is I'm just going to introduce it, assuming that in my data set I have just one observation. Okay. Actually, you can generalize it to having like a lot of observation, but just like for simplifying in order to simplify the derivation, I'm just going to assume that I have 1 point. Okay, so what we do in a VAE, I assume that I have x0, okay? And what I want to do is I have a model p theta, and I want to maximize, I'm going to try to maximize the log likelihood, right? I'm just going to try to maximize log of p theta of x0. The reason for that is that then if I can sample somehow from p theta, right, then if p theta has high likelihood around x0, then that means I will sample from things that are similar to x0, right? Again, if I don't have one sample but I have a data set, what I'm trying to maximize is something like this. Okay? Like it's just the sum over all of this, and I'm trying to maximize over all my data set. But again, just to clarify what I'm going to do next, I'm just assuming that I have one sample, that I have one example in my data set. Okay, so the way the VAE works is by saying, it's kind of related to the remark that, okay, we need to compress the representation. We're going to assume that what is the structure of p theta? We're going to assume that p theta has the following structure. So p theta of x, so let's say this is an image. This is going to be the marginal of p theta of x, z, marginalized on z, where this is like an extra, what we call latent variable, right? A latent variable. And the way we model this joint model here is as follows. We just assume, so here now, like instead of having a model of the marginal, I'm having a model of the joint, and I'm assuming that this can be written as p of z, and I'm only computing this thing. Okay? So the only part that is parametric is this thing here. Yeah, this is just the conditional. Usually this thing is chosen to be very simple, and this is just a Gaussian. Something that is important is the dimension of z doesn't have to be the same as the dimension of x. Usually what we have is the dimension of z is smaller than the dimension of x, right? Okay, so this is the model that we have. We just assume that we are given some kind of distribution in the latent space, and then we just model how to go from latent space to image space. Right? That's the goal. But then, okay, and how to do this? We want to maximize this function here. So this is the thing to maximize. This is the thing to maximize. Okay. So in order to maximize that, well, that sounds like hard at first. Up. Why is it hard? It's because we are trying to maximize the log of an integral, because log of p theta of x is log of the integral of p z p theta x even z, right? So like this is intractable. Even usually, sorry, something I should have said is that usually this thing, what kind of form we assume for that? We assume that this is some kind of Gaussian. So Gaussian in the variable x with a mean that depend on z. And sometimes we parameterize the, here I'm just going to assume that we don't parameterize the covariance matrix. Right, so this is usually the model that we have for the conditional distribution. And even if this is simple, because we are integrating here in the log, that's a bit nasty to optimize this stuff. Right? When we take the gradient, like things don't behave so well. So what we can do, and this is the whole point of the VAE, is to say, okay, actually I'm going to introduce this other distribution. I'm going to introduce this other distribution Q phi z x Q phi z x. dz. Okay, so I have just introduced, this thing was going from latent space to image space. This thing is going from image space to latent space. So this thing is the decoder, and this thing is the encoder. Okay, and I've just divided this stuff, right? And why am I happy about this? Well, now the nice thing is that I can leverage the fact that I have the concavity of the log, and so what I can use is that in fact I have log. I can put the log inside, and I have log p of z, p theta q phi z x q phi z x. So instead of maximizing this thing, what we do is that we are going to try to maximize this thing here. So what is inside of the integral, right? So this is what is sometimes called the elbow for evidence lower bound. Evidence lower bound. Right, and you can see now that like the nice thing with that is if I want to optimize with respect to p theta, then that's simple because I just need to sample from q phi. Usually we also assume that q phi has a very simple form, which again is just going to be some kind of thing that is parameterized in a similar way, something like that. And then we just need to do is we just need to sample from this. We take the gradient of the log of p phi, and then we can p theta, sorry, and then we can update the parameter theta. And we do the same thing. The optimization is a little bit more complicated, but we can still do it to optimize the parameter phi. So what we do at the end of the day when we do a VAE is that we optimize this in both theta and phi, right? Again, this is the decoder. This is the decoder. And this thing here is called the encoder. It's called the encoder. Right? So this is kind of like this is VAE in like 5 minutes, but that gives you the kind of idea of like what is the thing that we are trying to optimize. There is something to optimize with respect to the parameter phi. Usually what we do, we use something called the reparametrization trick to avoid having to take the gradient of the thing that we are against the thing that we are integrating with. So that means that we can rewrite that. We can rewrite this whole thing as some kind of integral with respect to a measure that does not depend on phi, and then it's easier to take the gradient. Right? That's kind of like the whole point. But at the end of the day, if I do a small graph to summarize what we are trying to do, we are starting from x. We can encode that with q phi, and we can decode that with p theta. Okay? Right. But that looks a lot like forward process and backward process, right? And that's the whole point of this other approach. So the other approach, that like the approach of Jonathan O, that I'm going to show you the derivation, but like right now I'm giving you like kind of the spirit of why it's very similar to what I presented you before, is that now, okay, imagine that instead of having just one latent variable, I had like a bunch of them. Like I had not only z, but I had z1, z2, z3, blah, 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 blah. So what I would have instead is something I'm going to replace I'm still doing the VAE, but like I'm just replacing Z by a bunch of other variables, and the way it changes my graph is that I have Z1, Z2, Zn. And here I have a Q phi, 1, 2, Q phi 3, Q phi n. Okay? And then I learn phi theta, phi theta, phi theta, phi theta 1, phi theta 2, phi theta 3, phi theta n. Okay? So now it, yeah.
You did a trick with dimensionality reduction in the latent space every time here, or there's like another funky thing to do so that it's like completely comparable to diffusion?
Yeah, so usually when we do VAE, the original motivation behind VAE was to say, okay, I mean, X has like a high dimension, I'm going to reduce the dimension with Z. Like now, what I'm assuming here, I'm going to assume that the dimension of Z, of all the Zi, is the same as the dimension of X. So actually my latent space is much bigger than like my image space. I'm going like the other way around, right? Because my like the latent space, if I were to consider this as a latent space, it would be Z, like the concatenation of all this stuff. And so the dimension of Z is actually n time the dimension of X, if you think of it this way. So.
And what's the benefit of having several steps like that instead of having only one step?
So that's, I mean, you could also ask that for diffusion model. Why do we do one step, several steps over one step? So this is linked to the idea of people call that sometimes iterative refinement, which is that when you try to learn how to go from a Gaussian to a very complicated distribution with just one network, you have to learn a lot because like you have to learn, let's say, how to separate the modes, how to reweight stuff. Whereas when you do this stuff in a progressive way, your neural network is only modeling like how to go from one state to the other, and the states are actually quite close to each other. And so you have the thing that like you're not in a GAN, for example, you're asking to go from one Gaussian to an image of the cat in one go. So the sampling process is extremely fast because this is just one application of the neural network. Here we apply the neural network n steps, so that can be quite costly. But on the other side, that can be quite costly. But like on the other side is that we get like much better fidelity. So this idea of iterative refinement is really what is key to make all of these models work. There is like to classify a little bit all of this generative model. There is this paper called Trilemma of generative modeling. And the way they explain that, and it's kind of a nice graph. They say, okay, so there are three things that we want from a generative model. We want it to be diverse. We want it to have like high fidelity. And we want it to be fast. So.
Are you gaining fidelity? Is your claim?
Yeah, we want, I mean, when I say fidelity, is like we want like good looking. That's more like, it's not like you're close to the, it's not, I don't want to memorize, but I want it to produce good image of cats and dogs. So usually, and if you look for something that is good at respecting the diversity and fast, so these two things, usually people say that like VAE, variational rental encoder, are really good at doing that. If you want something that has good fidelity and that is quite fast, here you have GANs. GANs usually produce like good-looking images and they are quite fast because this is just one application of the neural network, but they suffer from mode collapse in the sense that like usually they are really, really bad at getting the diversity. This one here, diversity and fidelity, that's diffusion model here. What they are missing is that at least the original one, they are not so fast. You need to apply a lot of time the feed-forward network, and that can be quite costly. A big area of research these days is how to make these diffusion models faster and like how to distill them into networks which are easier to learn, etc. And like, yeah, a lot of tricks are being tried right now. I think like distilling the diffusion model is something that is, something that is vital for like production application. Yeah.
The only problem then with VIEs is that the image is blurry, right?
Yeah, yeah.
Okay.
So that's why I didn't say they are missing the fidelity.
But why are they faster?
They are fast because you just need one application of the neural network.
For the hierarchical.
No, for the VA, just for the normal VA.
Right, but
For the hierarchical, no. For the hierarchical, you need to apply many times the neural network.
yeah, but I mean, how does it compare? Are they still blurry, like the hierarchical one?
No, because the way I'm going to show that the hierarchical VAE can actually is a diffusion model.
Oh.
So that's the that's the claim. That's so yeah, so you lose. You're not fast anymore, but you regain the fidelity that is here. That's the point. But the thing is that if you at the end of the day, the lesson is quite simple. If you do a few steps, then you cannot reach high fidelity, but you are quite fast. And if you allow for more steps of the neural network, you gain fidelity, but you are slower. That's the hard truth. But yeah, so now on to why is this model actually equivalent to a diffusion model? Well, except is there any other question regarding that? No, all good. Okay. Right. So I was saying, okay. So I have these things here that I need to train, and I have these things here that I need to train. Because I'm assuming, as you were saying, that the dimension is the same here, just for notational purposes, I'm going to rename the latent variable with x. So now it's starting to look a lot like the diffusion model I was talking about. And then, remember, like in diffusion model, Q phi was given to us, right? Q phi was just like a Gaussian noising process. It was just a small Gaussian perturbation. Here, I'm assuming that I can learn this thing. But in VAE, we assume that we can learn this thing, but we can also fix it. So if instead of being able to learn that, I just fix that to the Qk plus 1 given, well, actually here for this one is Q1 given 0 that I had before, then I completely recover the forward process of a diffusion model. And then I just need to model the transition density of this thing here. So the models are like very similar. The one thing that is different is like, is the training the same? Because like before I was like, okay, I justified everything with the 3D identity, blah, blah, blah. I need to approximate the score, etc. And the answer is yes. So the answer is yes. So up here, so this derivation here is exactly, this derivation here is the elbow. So remember, I did it with just one variable before. This is the elbow, but like with n variables. So this is the elbow for hierarchical VAE, okay? And as I was saying before, to make the link with diffusion model, we're gonna choose this distribution. So the distribution, the encoding distribution, I'm going to choose it as something that has this kind of Gaussian decomposition, and I'm going to assume that I have this for the transition, right? So again, the reason for doing that is that by doing so, we don't have to learn anymore the encoder, and we have something that is completely tractable to encode the data into something that is more and more Gaussian, okay? So first difference with VAE, I am not learning Q. Usually you learn Q in VAE, here I don't learn Q. What is also different with VAE, of course, is the fact that I have something that is hierarchical instead of having just one latent variable, right? So that's the thing. Okay, so now we have something that is actually looking quite similar to diffusion model, at least in terms of like graphical model, but is the training the same? Yes. So, sorry, the one thing, of course, the one assumption I have is that I'm going to parameterize like this small jump from k plus 1 to k in the same way I was doing with diffusion model. Like this is perfectly fine. This is just one assumption about how my model factorized. Like this is a model assumption. Like this, I'm allowed to make this assumption here. Okay. So when I write down the elbow for this stuff, so the elbow takes this a priori kind of nasty form here, but I can simplify it, and I have like two like boundary terms that I'm going to ignore for now. We can discuss that later, but like yeah, I do have like boundary terms that I'm happy to ignore, and I'm just going to focus on like what is the term here, and what I'm going to show is that the term that is here is actually the denoising score matching loss that I was showing you before. So you recover, you know, like we've gone full circle, and this will be like another justification of diffusion model, basically. Right. So again, how do I say that? Because like this is a lot of stuff. Let me check how I can blah blah blah. So yes, okay. So what I need in order to analyze this term here, I need to be able to compute this quantity. So this quantity, what is it? This quantity is the distribution. So Q, remember Q as like Gaussian transition, okay? Q as Gaussian transition, and now what I'm looking for, when you decompose the thing, you have that LK depends on Q at time K, given what happens at time K plus 1 and what happened at time 0. But all the Q's conditioned on zeros, they are all Gaussian. So in fact, like the next slide, which is like very, very busy with like notation and stuff, this is just computing what is the Gaussian here. Because, you know, when the distribution of Q given 0 are all Gaussian. So like when I look at Q of K given K plus 1 and 0, this is also Gaussian, and I can compute all the coefficients for that. So this is the only thing I'm saying here. This thing is Gaussian, I can compute its coefficient, and this thing is Gaussian. Okay? So don't look at the nasty derivation, but the main point is that yeah, so like, do I have it explicitly? That yes, that if I look at the what do I wrote it? Yes, so this thing here. Sorry. Yes, so this thing here is going to be. Sorry, I didn't write it explicitly, but. This thing here is the density. So you have like some parameters. Don't look at that. But you have a Gaussian expression for this Q of K given K plus 1 and 0. Okay. This is a Gaussian distribution that depends on xk plus 1, and that will also depend on x0. That's the whole thing I'm saying. And so this is for Q of K given K plus 1 and 0. Again, what I'm just showing you is this thing here. I'm just expliciting what is the distribution of that, but that's all what I'm doing. And then when I'm going to model my P theta, which is my generative model, the model that is trying to go from K plus 1 to K. So again, like the loss function is the log of P theta that goes from K plus 1 to K divided by Q that goes from K plus 1 to K, but also conditioned at time 0, and this is integrated with respect to this. So of course, like to make this equal to 0, I would like to take this equal to this, right? That would be the dream. The problem is, of course, I cannot do that because this thing does not depend on what happened at time 0, because I'm trying to predict what happened at time 0. So Q of K given K plus 1 and 0 is something that is Gaussian with a mean that depends on xk plus 1 and x0. And what I'm going to do, in fact, is I'm just going to assume the same form for p theta, so this was the form of qk, given k plus 1 and given 0. I'm going to assume the same form for p theta, except that now I cannot assume that I know the noise, but in fact what I'm going to do is that I'm going to estimate the noise given my position at xk plus 1. And now if you remember what I told you, what is the loss function that we are looking at when we look at diffusion model? This is a loss function that is estimating the noise that we have added to the data. And this is exactly how we're going to recover the loss function at the end. So sorry, the slide's a little bit messy, and I just want to not spend too much time here, but like the main idea is that like we decompose this elbow, we have this internal terms, and these terms we can express it as like Gaussian, and we have this special writing for p theta that I'm also going to be assuming to be Gaussian. And when I look at the loss function that I have, at the end, the loss function that I have at the end for every k look like something like this, and I have like extra derivation following that shows that this thing, when you expand it to the first order, this is exactly the denoising score matching loss that I was showing you before. So yeah, sorry for rushing a little bit through this. So hopefully you will have the slides for this. But again, the main point is that if you were not happy with my derivation before, you can recover it with the elbow. That's and like with a variational encoder perspective. So that's what I'm. Yeah.
Maybe one small question. So with the Q phi, you somehow learn a distribution over the latent space.
Sorry?
With the Q phi, you're learning a distribution over the.
So here I'm not learning Q phi anymore.
Okay.
Q is fixed.
Okay.
Q is fixed, and Q here corresponds to the forward noising process. If a good question would be like, if we now make Q phi learnable again, like what does it give you? And then this gives you like Schrodinger bridge, actually. So like if you want to draw a connection with optimal transport and like forward and backward SD, then this is hard stuff because you're also going to learn the forward SD that is noising your data. This is how you think of it as like, what is the forward, this is the equivalent of the forward noising process. Before we had fixed the forward noising process, so we do the same thing here when we have the VA in interpretation. And so we fix it to recover the diffusion model, but we could keep it learnable. And if we keep it learnable, then we have like a larger class of things to learn. But yeah.
So then the Fazit is then that you can kind of structurally change what you train and what you don't train from the hierarchical variation autoencoder to make it a diffusion model.
Yeah.
So it's not like the hierarchical variation autoencoder is not originally kind of the same, but you can kind of
exactly.
the structures
Yeah.
and the learning processes to kind of adapt it.
Yeah. So exactly. So you can see diffusion model as a very special case of hierarchical VA. Like this is a sub case of that, right? Like I'm making a lot of assumptions to fall back to diffusion model, but yeah.
Yeah, so unless it's a distribution, but you're learning the decoder exactly with the p theta.
Yeah, learning the decoder, we always learn the decoder, and in the case of generative modeling, p theta is like that corresponds to like learning the score type thing. Yeah.
But this is in the end gives you a distribution over the latent space, right?
Well, p theta, I mean, like the thing is that it's a bit weird to talk about latent space here anymore because the latent space is like this actually huge space of like all the intermediate step in the. So, in a way, yes, the p theta is going to map like all the noised level to like the one sample at the end. So, yes, in that way, it maps from the latent to the image space, but. Here, like latent is actually the opposite of what we usually think when we talk about latent. So.
And the p theta is then always assumed to be a Gaussian.
Yes, yeah. We in that setting, yes, we always assume it to be Gaussian. But that's also a very good question. when you're in the VAE stuff, like one nice thing is that, you know, well, that's also part of your remark as well. You could imagine, like, you know, well, you could parameterize that with whatever, Laplace kernel or like something else, and you could start to learn that. So you have like more flexibility in what you do with this setting. Yeah.
But if every p theta then okay, but the p set itself is not, right? This can be anything.
So p theta, like, yeah, all the p theta are like.
But the p set, so only the p set what you take in the beginning, like p set times the p theta.
No. This thing. Okay, so this thing is Gaussian, and the transition is Gaussian as well. But the whole thing is not Gaussian because the dependence here is non-linear.
Okay.
So that's the thing. The why the forward process is still Gaussian is because the dependency in the previous variable in the mean is linear. That's why the whole thing, you know, like when you accumulate all the steps, that's why it's still Gaussian. But like if you have a nonlinear model of something Gaussian and a transition that is Gaussian, then the whole thing is not Gaussian anymore, right? Yeah.
Because I was afraid that in the end it's
No. It's yeah. We don't produce only Gaussian samples. That's it. All right. So yeah, for the last hour, I'm gonna show you. We have seen that we've been productive today. We've seen like 3 different ways so far of interpreting diffusion model. We've seen the one with like defining a forward process and defining in discrete time, defining the backward process, and then by the way, it works, right? Yeah. Okay. Yeah. Defining the forward process, defining the backward process. We've seen the link with Anhild, Langevin, and the original approach from Song and Herman. We've seen quickly how to link that with hierarchical variational encoder. The last part is about how can I interpret that with SDs. So this will not be like I'll try to give some sense for those of you who might not be so familiar with SDs about what I'm gonna talk about. I won't give like again a very precise definition. That will take me like more than 1 hour to really dive into like what is the integrability thing that I need, blah blah blah. Okay, so the one thing I'm going to start again from my small drawing that I had before. That this is P0, and this is like a Gaussian distribution, and my goal was to define a forward noising process, right? Like that was the whole thing that I was telling you at the beginning, and I was defining that with a discrete thing. There is a way to change a distribution to a Gaussian one with a continuous process. The way we do it is like this. So I'm going to explain all the terms. I'm going to consider something like this, plus, okay, I'm going to do it this way, minus 1/2 plus dBt. So this is an SD. This is an SD. This thing here, this is a Brownian motion. So again, I'm not sure that everyone here is familiar so much with SD. So like, let me just explain. This part here is just the classical ODE that you would have, okay, in continuous time. This thing here is an extra term that we add that says, okay, I'm going to add a little bit of stochasticity. BT is a Brownian motion, so that means that when you can see that one way to think of it without diving into, okay, what is really a Brownian motion is how do we discretize this thing? When we so you know how to discretize this thing, right? Like discretizing an ODE, you can do it quite easily with Euler. So you would have something like this, minus gamma divided by 2 xk. Gamma is the step size. Okay. So now how do I discretize the dBt? Well, the discretization of dBt is done like this. And ZK RID Gaussian. Okay. This discretization here, this is called the Euler-Maruyama Maruyama discretization. Okay? So if you're not familiar with the theory behind SDE, you can just think of it as a way to make this thing continuous. One thing that is important here is the scaling. The scaling of the step size here is not the same as the scaling of the step size here. Basically what it means, the step size here is larger. Let's say that this is less than 1. The step size here is larger. What it means is that because you had all this stochasticity, this thing will not, if you just were looking at this stuff, it would have like a lot of regularity, right? It would be like a very smooth path. But because you had the Brownian motion, you lose regularity. And so basically this thing is, the class of this stuff is a C1/2 minus epsilon for every epsilon. Anyway, we don't care about the exact regularity of this stuff. The only thing I'm saying here is that when you look at these things, the trajectory will be something that is a little bit noisy, and the noise is given by this, which comes from this. And this is the effect of the Brownian motion. Right. This process I have written here, the reason I have written this one is this is what we call Ornstein-Uhlenbeck process. Or if you do machine learning, you call that VPSD. Right. The nice property of this process, so that's what I was telling you, I was explaining before, is that you can show, it's actually really easy to show that these things will converge exponentially fast to a Gaussian distribution with mean covariance, with mean 0 and covariance, the identity matrix. Okay? Yeah, I don't have time to, well, maybe I'll see if I have time to actually prove it to you. But the important thing is that it converges very, very, very fast to this Gaussian stuff. And that the rate of convergence is independent of the dimension. It depends actually on, it just depends on this. It like depends on the 1/2 coefficient that you put here. But that's it. In particular, you can be in very, very high dimension. It won't matter for this thing to converge as fast as you want to the Gaussian distribution. Okay? So that's the first point. If you care about this stuff, again, the rate of convergence is also independent of the dimension, no matter what you look at. Wasserstein 2, total variation, Kullback-Leiber divergence, chi-square, whatever. The Ornstein-Uhlenbeck process is one of the simplest processes you can have a look at when you look at stochastic calculus. And it enjoys a bunch of really, really nice properties. In particular, conditionally to x0, I know what are the solution of this stuff. So let's say, because yeah, of course here I need to specify that the initial condition was distributed according to P naught, right? If conditionally to x0, I have that xt can be written like this. Okay, so what does it mean? It means that we have what we call exponential forgetting of the initial condition. The exponential forgetting of the initial condition comes from the fact that I have this term here. Okay? Okay, actually I think I made a mistake. This is divided by 2, I think, and this is just t here. Anyway, you rescale the time, it changes, it's just a scaling factor. Anyway, so this thing is the forgetting of the initial condition. So when I had a question at the beginning, like what does it mean to lose information? This is what we mean by losing information. We lose the information about x0 with exponential rate. And on the other end, we are converging towards a Gaussian. And of course, like this thing is Gaussian here. And you can see that like with exponential rate, I'm going to converge to, this thing is going to converge to 1, and I will just have a Gaussian, right? So far, so good? So this is the continuous this is actually the continuous equivalent of what I was describing before, right? When I was telling you, okay, I can define qk plus 1 given k, you know, with a Gaussian transition kernel that was looking like something, that was exactly what I was writing here. That was exactly the thing I was, the discretization of this thing was exactly what I was looking for in the first place. in the first part of the presentation this morning. Right, okay, so that's the forward process. We like that, it's simple, etc. It enjoys all the nice property. In particular, the fact that this is explicit is quite nice. That means that in order to integrate my SDE, I don't need to run the SD. I can just use this formula. You give me x0, you give me x0 and t, I can compute exactly what is the conditional distribution. I don't need to run the SDE. So that's quite nice. There are not a lot of SD that you can integrate like explicitly like that, right? Like basically Ornstein-Uhlenbeck process and Brownian motion. Brownian motion, just the Brownian motion would correspond to put this equal to 0, right? That's just right. So we have the forward process, and now the question is, that's a general question. What happens when I try to revert that process? And this is where interesting things happen. So I have a process. Let's say I'm just going to consider t between 0 and 1. Okay, I'm assuming that at time 1 I have noised enough, but you can put you could look at a longer time if you want. Okay, I have this, and this satisfies an SD. Okay. Now the question that I ask is, for me, when I want to do the generative modeling, what I want to model is what I'm going to call yt, which is x1 minus t, the time reversal, right? Like what I want to do is I want to go backward in time. Okay, okay, so the question is, does this satisfy an SD? And the answer is yes. And I'm going to give you explicitly what is the SDE, and you will see that we recover again diffusion model. And I might even be able to prove what is the backward SD that we have. So I'm just first going to give you the result, and then I'm going to prove it. So this is a result that was known in the 50s. It actually comes from the stochastic control community. We were talking about stochastic control earlier. So I think it first appears in one of the lectures of Vollmer. And actually one of the lectures he gave at what's the famous Saint-Flour. Thank you. Yeah. So in the he gives like more. And it gives like extra link with the stochastic control stuff. Yeah?
Would you also be able to recover Fokker-Planck equation and then use the probability itself, or is it not useful here?
Sorry, can you repeat that again?
I know that from this statistical you can recreate the Fokker-Planck equation from the probability.
Yeah, yeah. I'm gonna use the Fokker-Planck equation to prove this stuff. Okay. Yeah, that's gonna be exactly what I'm gonna do in like 5 minutes. So this was Vollmer, like let's say, I think it was in the 50s. Then it has been recovered, it has been rediscovered a bunch of time. One of my, and basically under different condition, right? Like that's the thing is that you need condition on this SD to be able to time reverse it. One of my favorite papers is the one by Osman and Pardue. They are all called like time reversal of SD, blah, blah, blah. This one is in the 80s. And there is a very recent one, so there is this line of work by Christian Leonard and like a bunch of co-authors where they give like conditions that are more related to the entropy of the path measure of xt to invert, to write the time reversal. So these are like very recent work, like 2020. And yeah, I really like this line of work because it fits very nicely into the context of machine learning in terms of like what kind of assumption we have on stuff. So yeah, all of this paper basically showed the exact same form for all of this, just under different assumption. And then it's like kind of a matter of like what you prefer. This thing is like more functional analysis. This thing is more like stochastic control. And this is more like kind of probability theory, Dirzanov theory type thing. Okay, so what is this backward SD? Well, it turns out that if under a condition on the under condition on the SDE. Let's say I have a general SDE like that. So BT here is the drift term. I could put some coefficient here. I'm not doing it because it would complexify the whole thing. So bear with me on that. But YT is going to be the following. And I'm just going to, well, maybe, okay, I'm going to put something that does not depend on the position. It could depend on the position here. Like you could have multiplicative noise. I'm just not doing it because it would, again, make things more complex. But what you have is, oh, sorry, not this, up. Right. Okay, so this is exactly what you have when you look at the SDE that is satisfied by the time reversal of this stuff. Yeah. And now, remember what I had before. If BTx is just minus 1/2 of x, then I have minus 1/2 of x. So I have yt divided by 2 plus, and let's say that sigma t is equal to 1, plus grad log p 1 minus t yt dt plus dbt. And here now you recognize exactly the form. If I do again the Euler-Maruyama discretization of this stuff, then you recognize exactly what I had written, you know, when I was doing my dirty derivation with the Taylor expansion that I told you was like not very well justified. So all in all, you can see diffusion model as implementing this time reversal ID that has been around since the 50s. And it's just, before it was impractical because we didn't know how to estimate this stuff. Because this thing is the, yeah, sorry, I should have said what is PT. Should be kind of obvious now, but PT is the density with respect to the Lebesgue measure of xt, right? Right, and so, yeah?
How do the sigma algebras actually relate to each other from these two processes? Because, I mean, to what is y measurable? Because, you know, the first is somehow progressively measurable or whatever. And then, I mean, then you reverse the time process. So how do the sigma algebras,
yeah.
It cannot be the same filtration or the same structure of sigma.
Exactly. So this is where it differs from like a forward-backward SD. When you look at backward SD, you look at something that goes backward in time, but this is still with respect to the forward filtration, right?
Yes.
So here, like this is with respect to the backward filtration. So this thing is an SDE, and the filtration that you are looking at is the one that is given by x1 minus t and t between 0 and 1. So you take, and the equality, when I say this thing has the same distribution, this is the distribution of the process xt is the same as the distribution in terms of path measure. This is the same as as this thing. What I'm not saying is that these two things are equal almost surely. They cannot be, right? Like they cannot be equal in almost surely. They are equal in distribution.
But we don't care in our case, since we want to.
We don't even care about that in our case. In our case, we only care about the marginal. So we have more. We have like that the paths are actually have the same distribution, but we don't care. We just want, in generative modeling, we just care about like the marginal stuff.
It doesn't matter if it is not equally almost surely.
Yeah. Does that answer the question?
I mean, okay. I'm afraid that you know this continuous setting would be, then if we only consider single time points t, not a discrete version again.
Sorry, I'm not sure I got it.
I mean, you know, you say okay, because you take for every t and then the whole okay. No, I have to give up on this.
So the way, I mean, I can give you like some hints on like how people especially in Osman and Pardue, how they show this stuff. You look at what is, there is, when you have a weak solution of an SDE, you can reformulate that with a martingale problem. So you have a look at what is the martingale problem that is satisfied by XT for the backward filtration. And the martingale problem that is satisfied by XT for the backward filtration is this. So that's the thing that you show.
Especially for the martingale, you have in the condition the sigma.
Yeah, but like the sigma, that's for this filtration. That's the thing that is important. Yeah. Yeah.
The lower xt is equal to the lower y.
Oh yeah, sorry. Yeah, there is a 1 minus that. Yeah. Yeah. And same here actually. Yeah. Yeah, of course. Yeah. Yeah. So yeah. In Osman and Pardue, they show it with the by solving the martingale problem. If I want to catch my flight, I don't have time to do the proof here, but I can do the proof. I can do the proof where we show this actually. So I can do a proof based on the Fokker-Planck equation that actually shows that we satisfy this, but I won't be able to show that we satisfy this. But yeah, that will be the rest is in Osman and Pardue. Yeah. So okay, let's. Yeah. Sorry, my bad.
A bit confused, you maybe lost reference somewhere, but so if you want to do this for images,
Yeah.
when xt for each time point t is like a vector in where the components are individual pixels. This doesn't seem to make much sense because when you like all the pixels are independent of each other, you would have want some coupling, right?
So the way you noise things is independent. So like it was the same when I did the forward process at the beginning. I was noising all the pixels independently,
Yeah.
but when you do the backward, like this part is independent, like is pixel independent, but these things introduce some correlation between the pixel, and this is the network, and this is things where things are happening. Yeah, but I mean, there is no difference between this, and I mean, at the end of the day, there is very little difference between what I'm presenting here and what I was presenting this morning. The noising process is independent, but of course, because we started from something that was not independent, when we look at the thing backward, we need to introduce back the correlation, and this is done with this thing here. Other question? All good? Okay. So let me actually prove this stuff. It's to prove the fact that the marginal are the same. This is actually quite easy if you know about the Fokker-Planck equation and you don't care about the regularity and integrability condition. That's which I'm happily gonna do again. So, okay, just a little reminder about the Fokker-Planck equation. If I have a general SD like this, if I have a general SD like this, and I look at PT, which is the sequence of, the flow of densities of my SD. So basically, PT is the distribution of XT with respect to the Lebesgue measure. Okay, right, what I had before. Right. So now the question is, this is kind of like a particle representation of the evolution, right? Like this is like following samples. What is the representation of this evolution equation in terms of like what is happening on PT? Well, what is happening on PT? This is where we have the so-called Fokker-Planck equation. Fokker-Planck equation, which tells us that this thing is going to satisfy some kind of PDE, and the PDE is going to satisfy is the following. Plus sigma t square divided by 2, and the Laplacian of PT. Okay? So this is, I mean, not showing that, but like it's a well-known fact. Okay? So the evolution, this characterized the evolution of xt, of pt, sorry. You know, if you were looking at an ODE, this, you would have this equal to 0, and this would be just the continuity equation. If you just add Brownian motion, so this part is equal to 0, this part is equal to 0, then you recover the heat equation, and that just tells you that when you add Gaussian noise to your distribution, you have the effect of like smoothing the distribution with a Laplace kernel. Okay, that's all this equation is saying. Right. So now the question is, okay, I'm going to define the following family, Qt, which is going to be P1 minus T. So what does it mean? It means that I'm going to try to find the PDE for the time reversed thing, okay? And I'm going to try to find a PDE, and I'm going to see if this PDE is associated with some kind of SD. So right now I have gone from SDE to PDE. Now I'm going to mess around with the PDE to get a PDE for the time reversal, and I'm going to go back to the SD. That's the thing that we're going to do here. Okay. So I'm going to take the derivative. Okay, so let's do this. I'm taking the derivative of Qt. Well, the derivative of Qt, this is the derivative. Qt is P1 minus T, so there is a minus sign that goes out, and this is dt of P applied at 1 minus T. Okay, and now I have all of this stuff. So with a minus sign, so this is the divergence of Qt B1 minus T minus sigma y minus T square Laplacian of Qt. Okay, this is just applying a minus sign here. Right. All right. Right. So we are almost there, because you have that. You know, like this resembles a lot a Fokker-Planck equation, right? You have the derivative of Qt, you have some kind of divergence term, and you have a Laplacian term. The problem is that I had a minus before. The minus was telling me I'm smoothing stuff because I'm adding Brownian motion. Now I have I had a plus before, now I have a minus. And the minus is actually telling me I'm removing noise. This is like kind of the denoising operator that is happening here. So this does not correspond to an SDE, actually. And so what we're going to do is that we're going to slightly do a very smart manipulation that is the following, where I'm just going to say, okay, well, I have a minus. I don't care. I'm just going to say that this is minus sigma 1 minus T square Laplacian of Qt plus sigma 1 minus T squared divided by 2 Laplacian of Qt. I've used that minus 1/2 is minus is minus 1 plus 1/2. Okay, and so now this part here corresponds to the noising part. This thing is the same thing as this. It corresponds to some kind of Brownian motion here. Right, like you recognize this, except that I have reversed the time in the sigma t. But now, like the hard part, of course, is to deal with that, because this is not naturally written as a divergence. But we're gonna still be able to say something. Maybe can I put that? Yeah, a little bit more up, so I can keep both things. Yes. All right. So the last step is to remember that the Laplacian is what? This is the divergence of the gradient of Qt. Right? So if I rewrite this thing, I'm just going to rewrite what is in the square. This is the divergence of Qt B1 minus T minus sigma 1 minus t square, the gradient of qt. Okay? But then I can finally rewrite that by using that the gradient of the log of qt is gradient of qt divided by qt. So this thing is actually the divergence of qt b1 minus t minus sigma 1 minus t square gradient of log of q1 minus t. Okay? Is it all right for everyone, this step here? It's just using that sorry. Yeah. So again, this is by definition of the Laplacian. I just have to rewritten what I had before using the definition of the Laplacian to put everything in the divergence operator. Once everything is in the divergence operator, I want to put qt in factor of the whole thing. And by putting it's not q1 minus t, it's qt. And by putting qt in factor of the whole thing, the gradient becomes the gradient of the log. Right? Again, this is just that gradient log f is gradient f divided by f. Right. So if I rewrite the whole thing, I get that the PDE that satisfies qt is minus the divergence of qt b1 minus t minus b1 minus t plus sigma 1 minus t square grad log qt plus sigma 1 minus t square divided by 2 Laplacian of qt. Right? And what I had said before, can I put both on the same? Yes. I had said before, okay, if I have an SD that satisfies this stuff with drift BT and covariance matrix, volatility matrix sigma t, the Assidis-Fokker-Planck equation is this thing here. Well, now what I have is I have found a way to write qt in the form of a Fokker-Planck equation where bt is replaced by this stuff and sigma t is replaced by this stuff. And so that tells me that qt is associated with an SDE, and the SDE is given by minus b1 minus t yt plus sigma 1 minus t square grad log qt dt plus sigma 1 minus t dbt. Right.
Was this 1/2 thing arbitrary? Because you could have split it otherwise, right? You have put one Laplacian.
I was like, I have 10 minutes remaining, so that was exactly what I was going to talk about. Yeah. Yeah, it is completely arbitrary right now. Like the reason, like this is just aesthetic, right? Like because I recovered, if this was constant in time, I would recover the same coefficient between the forward and the backward. But yeah, I could do something. And this is aesthetic and not. So if you split it in another way, you won't get the equality of the path measure. You will still get equality of the marginal, but you won't get equality of the path measure. Not that we really care about that for generative modeling, but when I do it this way, you don't see it in the Fokker-Planck derivation because the Fokker-Planck only care about the marginal. But if you were to do the Haussmann and Pardoux derivation, it would be clear that there is only one way to do this stuff, to do this splitting. But yeah, like this basically tells you that the distribution, like the conclusion of that is that the distribution of 1 minus t is the same as the distribution of xt, and if you follow this SDE. And for me, like there is the nice interpretation, you know, like in terms of we were looking at a PDE that was doing some kind of, instead of adding noise, this was corresponding to a denoising operator, and in order to still add noise in to get the backward SDE, we did this splitting step, and this became like noise. This became this noise here that we add, and this became the denoising operator that arrives here, and that gives us the grad log qt here, and we've seen, with the denoising score matching laws that this was in fact corresponding to a denoiser. So like for, like kind of like.
In fact, it is the strength of the noise that you get to put here. In the splitting, you put some strength on the noise.
Yeah, yeah.
In the decoder.
Yes, exactly. So that's why you can choose over decomposition, and in particular you can also you can choose to put no noise. That's what I was gonna show in the next to get something that is not an SDE but that is an ODE actually.
And what is the influence on diversity fidelity of the noise, of the strength of the noise?
It's a bit. I don't think there is like a. So I mean, theoretically there is none. Like because it's all the same Fourier-Planck equation. So like there should be none. In practice, I don't think there is that much of a difference, but usually we get better quality results using the SDE than using the ODE. The nice thing with ODE, I mean, I'm going to talk more about that right now, but the nice thing with ODE is that there is now a one-to-one mapping between the Gaussian and the image. And so we can do interpolation in the latent space, we can modify things in the latent space, and then we have more control about.
Maybe we are more robust, or maybe we control more.
So there is that, and like in terms of robustness, it's when you have all this distillation of distillation of diffusion model, this is always a distillation of the ODE process and not a distillation of the SDE, because if you try to distill an SDE, you need to distill the noise. So basically, you have like some kind of Brownian tree or like something that you need. There is like this extra knowledge of the noise that you need to keep around. If you have an ODE, you just need to distill the drift.
If you have an ODE, you are also more mathematical property as mutuousness, or you can quantify robustness, or you can do more things.
Actually, the SDE is easier to analyze than the ODE. Because it's kind of like, I mean, I'm by no way expert on that, but it's kind of like, when Pierre Williams was studying like optimal control, he was adding this kind of viscosity term with this extra Laplacian that corresponds to adding like a bit of stochasticity, because it regularized things. The Laplacian has the nice property that like the PT are going to be more regular. So the theoretical analysis of this stuff is easier to do with SDE. Especially when you look at tools from like control theory, and there is also there was all this trend from like the statistic community by Andrea Montanari, etc., of stochastic localization, and stochastic localization is much easier to analyze in the stochastic setting than it is in the deterministic setting. So that's why usually when we look at there are much more work on like the analysis of the good behavior of the SDE than there is for the ODE. And usually the results are weaker for the ODE. One point is that you're talking about Lipschitzness. Controlling the Lipschitzness of this stuff, even in very simple cases, is like incredibly hard to do actually. Yeah, it's something that I think is still quite an open problem, especially like usually we try to bypass actually this. We try to bypass to have to control the Lipschitzness of this, because it's not even true that if you start with something that is gradient Lipschitz at the beginning, if you noise it with Gaussian noise, it might not still be gradient Lipschitz, which is like something that is kind of like counterintuitive, but yeah, it's very, very hard to control how the Lipschitz constant of this thing evolves during time. So usually we use other tools, again, like Girzanov theory basically to control this stuff. But yeah, because this thing is not very well behaved. Okay, so in the last minute, I'm just going to show you that I did this trick here with the minus 1/2, which was -1 plus 1/2. I'm just going to show you quickly how we get to the ODE. This is very, very simple now that you've seen the trick. So instead of doing this thing, I'm just going to put all of this into the divergence. So if I put all of this into the divergence, what I get is that the divergence of Qt is B1 minus T minus sigma 1 minus T squared divided by 2, gradient of the log of Qt, right? So this is I don't have the Laplacian term anymore, so I don't have an SDE. This thing is the continuity equation of an ODE. And actually, I'm going to put the minus here, plus here. And so I can also describe Qt with an ODE, and the ODE is given by this. So minus B1 minus T plus sigma T 1 minus T squared divided by 2 gradient log P1 minus T dt, right? And so if you compare with what I had before, here I had like just sigma 1 minus T squared. Here I have sigma 1 minus T squared divided by 2. But this thing is an ODE. And basically we like that. We like that for several reasons. One of the reasons is, as I was saying, because this is an ODE, there is a deterministic mapping between the latent space, well, the Gaussian space, and the image space. There is another thing, as I was saying as well, that it's much easier to distill, to like apply knowledge distillation to an ODE than it is to an SDE. If you want to have like fast sampler, there is more theory or like more methodology around how to do this for like ODEs compared to SDEs. The one thing that you lose though is the fact that the ODE and the SDE have like very different paths. Again, so I just want to emphasize that if you do this, you will preserve the marginal, but you will not preserve the path measure. Okay, and yeah, that's basically the one thing. And I will just conclude by saying that once you have that, this thing is just an ODE. If you have, we've computed that with the denoising score matching loss. We have access to this thing. And then you can compute the log. If you want to compute the log likelihood of your data, you can do it the same way you would do with a normalizing flow, because this thing now is just a normalizing flow. It just has not been trained in the same way of a normalizing flow, because normalizing flow are trained, by maximizing the log likelihood in some kind of way. We've done that in another way with diffusion models. But what we have is that at inference time, this thing I can use it to compute the log likelihood of my model. And so in example where you want to run the evaluation of your model and you don't have like, let's say, the fit score, you don't have like nice perceptual evaluation, and you can only rely on the log likelihood, this is the thing that we use. We use the ODE representation. Right. Okay, so yeah, I think I might stop here actually, and we have a little bit of time to take questions.
Yeah, first of all, thank you very much. It was a very nice opening for a week-long conference. So I think we have time. Yeah, we have time for comments, questions, remarks.
Yeah.
Yeah, thanks a lot for this very nice presentation. Question about the distribution. So the focal point equation describes the evolution of the density.
Yeah.
But still, at time 0, the density might have a support on a low-dimensional manifold. So to me, there is something strange saying that it jumps immediately from a small-dimensional support density to something which has 2 dimensions.
Yeah.
So how does
The answer is that I've lied to you the whole time, and like what I've said is only true if P0 has like the same support as the Gaussian, right? Of course, because otherwise the deterministic normalizing flow cannot create this kind of separate the manifold structure. So what we usually do is either we assume that we have like full support, or we do the denoising up to a little time t. And then we say, okay, we've denoised up to a little time t, then these two things, the little time t and P0 are actually very close in Wasserstein distance, and we control it like that. Even like for stability issues, we never, because this thing, because if you are supported on the manifold, these things will explode because there is no density, right? So this thing is actually not very well behaved near time 0. So when we run this in practice, there is always some kind of numerical stability epsilon that we put, and we never run things up to time 0. But yeah, I mean, like that's a very good remark that like if you don't have the same support, Like there is no way that we can go back to the like from a Gaussian to something that is not fully supported. Yeah, for sure. Yeah, yeah. But that really shows in the analysis. Like when you do the theoretical analysis of this stuff, we always have this kind of assumption, either that we have full support or that we don't go back to the whole process. Yeah, yeah. Yeah. So in 2022, I had this paper where I was analyzing that is called convergence of diffusion model under the manifold hypothesis, where I tried to analyze the behavior of this in Wasserstein distance. So like really when you assume that the distribution is like completely supported onto something that might have like a lower dimension, and I had to do this type of assumption, and then the hard part is like to control the behavior of this stuff when it starts to explode, and show that if you do things correctly, like things will be nicely behaved in the discretization, basically. Yeah.
What about other kind of data? You mentioned, I think, text generation very briefly at one point, or what about discrete data?
Yes. Yeah. That's the next frontier for diffusion model. In terms of text, it's still underperforming compared to like LLMs and like transformer-based autoregressive model. There are some efforts, published efforts on like trying to use what I've written here. I've written it for an SDE. It's actually true if you have a continuous time Markov chain as well. You could derive the same thing. You can derive it for a jump Markov chain. You can derive it on a manifold, etc. It's very, very general, in fact, this result. So you can, if you find a new process, you have a new paper with this time reversal, and so you can do it for the discrete stuff, but for some reason it still doesn't really scale. And I think one of the reasons is that it's not clear what is the iterative refinement and what is the forward process that we should be using in that setting. But it's quite clear that Gaussian works for images. What should I use to noise text? People use masking usually. So you just randomly mask the token, but you can show that this is probably not a good idea, because then your model becomes equivalent to a permutation invariant autoregressive model that we know are not performing that well. So like there are still a lot of exploration to be done here. Like I don't think we have something that is perfectly working. So that's for discrete data is not there yet. Everything that is manifold data, it works really nicely. And everything that is like in RD, it works nicely as well. But yeah, the thing that doesn't work is kind of discrete data. Yeah.
So that already partially answers my second question, which maybe what is currently somehow the frontier? What are people excited about? What is needed?
Yeah. So I mean, I can tell you what people are excited about and what I'm excited about. So that's there is some intersection, but it's not complete. So I think like there is a huge push to make these models faster, instead of like fewer NFE, so fewer neural function evaluation, because it's quite costly from a production point of view. We want to use less evaluation of the neural network, so that implies distillation, faster sampling. All these methods that like there has been quite a huge push on that last year and this year, I would say. So that's one of the area of interest. And I think like we still you cannot win on every front. If you reduce the number of function evaluation, at some point you have to lose the fidelity. But somehow, if you could control better the trade-off between these two things, that'd be great. Discrete data, that's one of the thing. What else? I think like still for like application specific in like science and stuff. Again, what is the good forward process? What is the good model that we have? Especially for protein design and stuff like that. I do think also that for the sampling procedure, right now we sample the sample independently. We could introduce some kind of correlation to make them like repulsive in a way, to like explore the space better. And like it would cost, you will have like try to avoid the memorization problem basically, because I think the memorization problem is here to stay, and there is like a lot of opportunity here. And then on like the theory / methodology side, I didn't talk at all about it, but like everything that is linked with optimal transport, Schrödinger bridge, like really when we care about the path, what can we do here? this is the type of thing that I think is like quite promising, because it's not generative modeling. It's like other tasks, like transfer tasks, going from one distribution to the other. But it's not very well explored yet. And I think like right now the algorithm that we have, like they are okay, they work, but like I think they could be improved by a lot to like make them more scalable, basically. Yeah. I think I'd say that's it for this. Yeah.
Maybe Nosumi, yeah.
I'm not familiar with normalizing flow, but I'm trying to figure out what the gradient of logarithm of p.
Sorry, the gradient?
Gradient of logarithm
Yeah.
p. Is it related to adjustment about partition function?
I mean, this is the gradient of the log is the thing that we're looking, like this is the Stein score that we're looking before, right?
Stein score.
Yeah, that's the thing. You know, when I was looking at denoising score matching, this is exactly what I was trying to estimate, this thing. And you know, I was using this thing that I call the Tweedy identity, etc., to estimate that.
It is related to probability distribution change.
Yes.
And you want to adjust such change by gradient.
Yeah, yeah. So this is the denoising stuff that I was telling you about, that I was, you know, like this act, this thing is equivalent to like applying minus the Laplacian. Like this was this thing here. This is like running the PD backward in time. Yes, yeah, exactly, yeah.
So is this horizontal or vertical? No.
Yeah. I mean, when you look at it like this, it's vertical, and then it becomes horizontal when you look at this.
All right. Yeah, before thanking our speaker again, let me say tomorrow we continue with neural ODEs. Yeah, so with SDEs, ODEs tomorrow, neural ODEs, SDEs. So hopefully see you all at 9 o'clock tomorrow. And yeah, let's thank Valentin again.
Yeah, thank you.